Great. Hey guys, welcome. Oh,
Just to confirm, this is the States accounts and not personal accounts?
yeah, this is Zoom logged in, so it's recording to the the Zoom cloud. All right. Hey guys, welcome to CDR. Thank you all for being here. If you're gonna play video games in that row, don't be here, please. I'm looking at Drew Brian right now.
I was like 5 minutes. Not bad.
Thank you all, senior members, for being here, and people during like the last week of classes when finals are looming and Mitchell looks stressed. So today, just because of Circuits Lab Practical, we have to have payload go first and do payload first entirely. That couldn't have been changed, so we have to do that. But other than that, we're going to go through it as we normally go through it. Forward. So first, sign in. While you sign in, I'll talk to you about some of the logistics. As usually, we have the asking and responding to questions. That is intended for people who want clarifying questions about how a rocket works, what the acronyms we're using are, why you have a low launch, things like that. Any technical questions you will save for the second run through. We will go slide by slide. We will jump to the first slide where people have questions, and we'll run through it like that. Question?
Can you put both of those links in the Slack?
They are, yeah. Can someone do that while I'm talking? They're both, if you go onto the slideshow, you can click the pictures and they're attached to the pictures. Yeah, newer members or people who just have questions, feel free to use that. Older members, if you could keep a tab open while you're listening, that'd be great. The last thing I have to announce that's logistics-wise is the name of our rocket. So some of you may know this, some of you might not know this. For the past, I mean, for as long as we've been launching, we've always gone to Ben's farm. Ben had a dog named Aurora. Recently, we learned that Aurora passed away. So I talked with Ben at launch. They're comfortable with us naming our rocket Aurora. We are still working on the details of the payload, just because we have to check with like what Ben wants. It'll be something along the lines of like Aurora's used to hunt rat and mice, so it'll be something like that, something fun like that that'd be like inside of Aurora. So that's our rocket and payload name for this year, and designing will start promptly and is already underway.
The question
Are you signed? Okay, I'll check that one. There we go. Great. Any other questions? Okay. Oh yes, Jacob.
Oh, who's taking notes?
For the first run through, you don't have to worry about it. It'll be like the same thing last time. But for the first run through, you don't really have to worry about that. Payload, get on up here.
Yippee. Okay, yeah, come over here. All right. Hello, everyone. We are Payload. All right, so overview of what our payload experiment is hoping to accomplish. We're testing a thermoelastic polymer from Gary Winnick's lab and testing its vibrational dampening abilities using accelerometers. Here we have some of our CAD. So we have the external 3U CubeSat. You can see the external view. We have the exploded view that gives you a little bit more of how of an idea of how everything is put together. So where the bolts are going to go, how all of the external frame fits together, as well as how the accelerometers are going to be secured inside the payload. And then we have a more put together internal view. So you can see there. So we have, these are going to be our accelerometers inside of these little capsules. There's 2 on the bottom and 2 on the top. Along this back wall, we have all of our electronics mounted nicely there. We have our battery right here, closer to the bottom for safety reasons, an LED and a screw switch right there. So, theory of operations. The LED is going to illuminate, showing that the payload and hopefully all the electronics are running. During the time on the pad, we're going to start recording data. Then upon launch, data is going to continue to be recorded. We're going to record all throughout launch, recording those vibrational data using the accelerometers. And then that data is going to be stored and we'll be able to collect it upon recovery.
So the materials we're going to use, payload is going to be, the frame is going to be 6061, like it was in previous years, or I think it was last year. we're gonna have a window this year, that's gonna be acrylic. Then we're gonna have the mounts for payload are gonna be 3D printed on the resin printer. In ThinkBox, that's gonna be high temp because it's the stiffest. Then we're gonna do Petri for the electronics and screw switch mount. And then for the window, we're gonna attach it with some brackets. And with some screws.
Cool. So a little more of an section view of the internal components of the CAD. So as I mentioned previously, we have accelerometers on the bottom and on the top of the payload. So this gives you an idea of how that's going to look. So these outer capsules are going to be what's made on the PolyJet using resin. Inside the accelerometers, one of them is going to have the polymer, and then the other one is just going to be the accelerometer inside of there. And then moving to the next slide, this gives you the top view, how they're secured to the top, kind of hanging upside down, and it's going to give us some interesting data to see, like one suspended in midair versus one just like kind of resting on the bottom. So we're excited to see that. All right, so I know everyone has been very curious about what this polymer actually is. This was information directly from the lab. This might have to be cut from the recording because it is not, it's a patent pending study right now. So tri-layer dampening system using SIBS. It's a thermoplastic elastometer, and it encapsulates a viscous layer. So it kind of is similar to rubber, but at different temperatures, it gets harder like glass, or it becomes more viscous at higher temperatures. Around below 0 degrees Celsius, it becomes like stiffer. Its optimal operating dampening range is 60 to 80 degrees Celsius, where it's more rubbery and flexible. And then once the temperature goes above 80 to 100 C, it becomes a little more viscous, but it doesn't melt. So we should be good with the temperature range that the rocket should be experiencing. This is Jacob for scale. So the polymer has one of the accelerometer models that we 3D printed in ThinkBox, and we have I think 5 polymer samples right now, and we intend to use those for testing. We would like to test piercing, how much it takes to tear it, how much heat it can actually withstand before it begins to change, so things like that.
These electronics assemblies are a little more in depth. So everything's all of the most of the breakout boards are gonna be on this one 3D printed panel, and they're gonna be screwed in via heat setting tips on studs. So the accelerometer is on the top and bottom, and then everything's arranged in a way for better wiring. Like the battery goes to the screw switch, which goes to the buck converter, and then that should be wired nicely. And you have the other electronics. So for the electronics, everything's gonna go to the microcontroller. Like I said, everything's gonna be easy wired. I don't know if you can see in this last one, we're gonna have an LED. I don't know the label. There's an LED that's gonna go through the hole in that you screw the screw switch into. It's gonna be visible. It's not gonna go through, so you'll be able to see when it turns on, like Veronica was saying. Like I said, everything's screwed in 40 number 4 screws. And then the back panel is screwed into the wall. These are the electronics we're using. So we're going to use the specific that accelerometer is the best because it has the frequency we want, which is like 20,000 hertz. And then it doesn't really have much current draw. The biggest current draw is the accelerometer and the flash. So they're all SPI mostly. Same with the breakout, and then this is I2C, but it should be fine. Like again, it doesn't have much current draw. That has a bunch of current draw. It has 200 milliamps, but that's only at the end. We're gonna once we are doing recovery, we're gonna put an SD card into that, and then get all the data out, and then analyze it. So for data transfer, like I said, 20 kilohertz at 20 kilobits per second. Same with the thermometer, and then we should have more than enough spaces to all that, since we're only recording a 20-minute time frame from launch that we detect. it should be fine. So now we have much more than enough. So we're only gonna have one 18650. It should be more than enough, but yeah, we only have one. This is the circuit diagram. How everything's wired up. It might be a little easier to see on this one. Give you a minute to look. So that's on the SI see everything else is connected to down the plane and the clock and everything.
So here we have how the payload is going to be connected to the rest of the rocket through with this upper bulkhead, and we connect it using 1024 bolts, as you can see in the CAD model here. So now we have a bunch of FEA that we did on all of the external portions of the payload CAD. All of them had a relatively high FOS, everything above 1.5 to 2. So with the forces that the payload will be experiencing, especially the one on the bulkhead is probably the most important. According to the FEA, it would not break, so that's good. So right and left side panels, 6.3 min FOS for those forces. Backside panel, 5.2 min FOS. Other side panel, 6.7 min FOS. 0.1 millimeter min displacement. And then lower bulkhead or lower panel 3.9 min FOS. So everything's above 2. So then we did thread shear and bolt shear calculations for the 1024 screws that we're going to be using to connect. This is just for the connection to the bulkhead because that's where the screws are going to be seeing the most force during launch and the flight. Both of them had an FOS above 80, so I think we should be fine. Yeah. And that's the only thing on the payload that didn't break last year, so. Risk matrix. So, one of our failures, the bolts from the bulkhead could fail. Big consequence, likelihood, not very likely. Our mitigation for that was doing the bolt calculations and getting a very high FOS. Both bolts inside of the payload failed to secure things correctly. Consequence, really bad, 5, everything's flying around. Likelihood, very low, same. We didn't run calculations on those bolts. We can, if necessary, but those bolts will experience very little like outside forces, I think. So it should be okay. Payload electronics failed to turn on. That is a little bit more likely. Hopefully the mitigation of the LED inside will be able to prevent that. But if things don't turn on correctly or disconnect in some way, then we will not be able to collect any data. Data does not get correctly stored. Little less likely if all of our electronics, and we're going to run tests before putting the payload into the rocket to hopefully mitigate this. But that would be bad because we want to collect some data. Wires disconnect in the rocket. Same thing, we're going to test before placing everything in the rocket to make sure that all of our connections are good. Polymer ripped or torn. The polymer we're going to test how much it takes to puncture it, how much it takes to tear it. And even if it does, there would be a hole in it, but I don't think that would affect the overall like dampening in an exceedingly like negative way because the accelerometer would still be mostly secured with inside of the polymer. So a little bit less of a consequence. And then the polymer melts or becomes more brittle from the temperature ranges. Once again, we're going to test that. We could put it in an oven to see how much temperature that this thing can actually take. And so, yeah. And then compliance matrices, these will look very similar to PDR. Not much has changed. But if you just want to take a quick look at that. Experimental 5. Projects a relevant experiment. Weighs no less than 4.4 pounds. And I think that is it. Okay. Cool.
Thank you. We are gonna do questions.
Yeah.
Immediately.
Yes, I do.
Let's go back to the stairs.
That was close. It's already 5.
5.
Anything before 5?
Yeah.
Oh, wait, yeah, we need 2 seconds for people to load on this, so you can do something, yeah. Is the for the LED, so you might say that sorry now, is the hole because of it big enough? And also like the hole in the actual pit, are they both big enough that you will be able to see through to see both the screw switch and see the LED?
Yeah, I think it should be because with the LED, it should be bright enough that just having it be on and like being able to like have it even at the edge of the hole, if it's like illuminated, we'll be able to tell.
Yeah, you could mount it on the window and then not really mess anything.
Yeah, we are. It is away from the screw switch though. That's something that.
No, like if you put the whole assembly on the window side, then there's no, then you only have to look to the hole in the pocket and then you'll see it,
Okay.
so you have to peer through.
Yeah, because I don't remember what the specific rule is, but you don't wanna like put your face directly next to the tube when you're trying to 4
Right.
inches away.
Okay.
Yeah. Although this is when we could turn on before it goes vertical, right?
There's no like internet, so we can turn this on first.
Yeah.
Is there a reason using LED versus like a beeper?
There's no.
Because like a beeper would just eliminate the need
Well,
for.
I would think that if you can set up an LED correctly, it would be better because we're gonna have ends like computers in the rocket that each have their own beepers.
Yeah.
You were just saying you can turn it on before you get to the pad. In the event that you turn it on, get to the pad, get sent back, is your data collection still gonna be okay?
Yeah, we can stay at the pad for 30 hours. So that.
Okay.
Yeah.
Yeah, I would think.
So, there you go. With one battery, that's pretty
Need
good.
it turned on.
And you have enough space. Space for data collection.
Over
Yeah,
the.
well, not.
Oh, you
don't
don't
want to.
Yeah, it doesn't trigger until.
Can you walk through like the decision to put the accelerometers and almost cap? And still like
What do you mean?
Like-
Like, like
that, yes.
inside.
Yeah.
So we wanted, we needed a way to secure the accelerometer so that they're not bouncing around inside of the payload. And so that's mostly what the function of the capsule is. We also, when deciding on the material, we wanted to pick a material that isn't gonna also have an impact on the dampening. Like if we were to use certain infill, if we were to 3D print it, then that could potentially result in not necessarily just getting vibrational damping data from the polymer, but also from the container. So that's why we decided to go with resin. Is that?
Yeah.
Okay. So it's mostly just containment. We didn't want the polymer just out and about, like screwed onto the side of the payload.
You don't have any on
Any other
stage?
questions?
Yeah.
Bob?
Is there, oh, sorry, number 5, is there like a channel or something to run a wire from the battery to the function?
Yeah, might be able to see more on the other one.
That one?
There, you can see there's a channel at the top of the battery, like when I said I had it.
So is that on the other side? In slide 5, like in the CAD itself.
It might just be too small of a picture, but like,
Yeah. but-
it's on the cap,
Well,
so.
So looking at the cap that goes over your battery, there's no
Oh.
hole in
I
that.
think it's at the bottom. If I remember.
Okay, anyway, like figure out routing, cause you have to,
That's
like
not-
that one battery powers all your like controllers and both accelerometers at the bottom and the top.
Yeah.
So no matter what, you're gonna have.
Yeah.
Like, I'm not.
Yeah.
Put some like real thought into like physically wire routing, like wire routing inside this, because
This is so much happier than last paper. I think
Oh, man.
chance will be significant, sufficient. Not saying it's a good idea, but probably would be okay.
Yeah, you definitely could get away with it.
You
Like,
could get
it's
away with
spaghetti, but that's gonna be horrible to work with.
Cable management.
You can see inside the paper. You don't want to see inside the paper and have it just be.
Wires.
Yeah.
Correct.
That looks bad to the judges.
Mhm, mhm. Gotcha.
Put up a sign.
We got to the number 7.
Number 7.
Six.
Six.
So you say during time when pad data is being quoted, you just said there was launch protection. So which one is it? So is data being recorded on the pad or no?
No.
Or is it?
We wanted to do like about 20 seconds before launch because having that as like a constant, like not a constant, but like a control for when there's no actual vibrational data yet, and then once launch is detected, it'll start storing the data.
Essentially.
Yes.
set file.
Exactly,
So
a buffer.
So you have a circular buffer. kind of
Correct.
thing.
Correct. Any other questions on this slide? 7.
Why are you using acrylic and not polycarb for the window? Polycarb is generally more.
Is that what?
Well, it doesn't shatter. That's the part I'm more worried about. We can't see it, but
Good questions, I.
Why are you using acrylic and not polycarb? Generally.
yeah,
We did.
just
There is one
Because it
advantage to using, so is that you can actually kind of.
you have it with water.
Yeah, but the water jet is down.
No, it's not. You
It
need
might be.
one of them.
It shouldn't be.
Maybe I have something in my head. Also, like, why are you using two different types of, like, 440 volts?
Oh,
They do.
Don't you need socket heads for the frames?
yeah, because
They do
they're
get it.
smaller. And the socket heads need to like fit inside so that it's like flush with how the frame is being assembled. While the button heads for the internal components can kind of stick up a little, makes it easier for disassembling it if we have to take it apart. Yeah. Any other questions? Next. Where this? 10?
9.
9.
For this is kind of jumping ahead a little,
You're good.
but I know there's screws that go into the bulkhead that's how you guys attach,
Mhm.
and there's like a little cutout in the holder is so that they can go in. Are you gonna put the screws in before you put the holders on? Because otherwise the gates go in.
Yes, they go in during integration.
Okay.
They just be sticking out until it all gets put together.
And then you put the holder on.
Mhm.
Okay. And
Yeah.
are you gonna Loctite that?
The
Slightly.
screws?
Yes.
Yeah, yeah.
Yeah. Cool.
Just like, not like a thing,
Mhm.
exactly. What is the reason you have accelerometers both at the top and at the?
More data.
It's
Like-
at the top it'll be a high frequency, less like it's different amounts of vibration.
And just to be,
On the end of the cable that isn't connected to the bulkhead is gonna.
yeah, it's gonna have
It's a pretty-
more vibration. Exactly. And we want to see that it's like not just like if we had one set inside the polymer and then outside, we have one set of data, but how do we know that it's actually like the like polymer dampening the vibration? Whereas having two is kind of like just more data, more confirmation of the dampening effects of this thing.
When you're actually operating this, is there like, it's probably kind of a good question, but like, is there gonna be a plan for like if one set fails? Or like, is there a way to like prioritize the set as
Right.
opposed to the other?
Right.
I know theoretically like a wire comes up.
Yeah.
Just don't get that.
Yeah.
But
I think there's
I
a
don't know if there's like a way for you to like prioritize one set as opposed to the
Wonder
other.
if
Or
maybe
that you
not-
can't, like,
yeah, maybe not like prioritize, but wire them so that if one of them were to come undone, we could still get data from the other three.
yeah, something like that.
Yeah.
That goes back
Yeah, exactly. So that would be the plan, to wire them such that we can get the data is each individually from each little packet, and so that if one becomes disconnected, we don't lose data for all of them. Yeah. Perfect. All right, next slide.
Factor 11.
Let's pair 11.
And,
Yeah, so you said if this says pending, and
Yes.
it's like, oh, we can't possibly report this sign, but it's your plan, like, actually writing the report, if you can't talk about it until we.
We're gonna talk with Dr. Winnick and see what kind of permissions we can get. I think all of this that we've like what it's made up of and the temperature that that it like is like works best at should be fine. But we're gonna talk with Winnick and the people working at the lab for what we are allowed to talk about and what they don't want us to talk about as well. Yes.
If your properties are temperature dependent,
Mhm.
do you wanna control the temperature? Like, is it weekly temperature dependent, so it's fine?
Yeah. It's weekly temperature
Okay.
dependent. The rocket inside hopefully doesn't go above 140 degrees Fahrenheit plus minus 10. And so that's well within the range of the optimal functioning of the polymer. And then when it goes up, it's gonna get a little colder, but I don't think it's gonna like
So as long as you measure the temperature.
yeah. Yeah, and we have a thermometer.
I was gonna
for
say,
that.
you do have a
Yes.
thermometer.
Correct. So we will know how it changed with temperature as well. Cool.
11.
11.
Yeah, take a wonderful picture first of all. Second of all, I guess this could have been on another slide, but I just chose slide 11. How exactly does this fit, like attach, like how is this secured in your capsules? Like I see the screw holes. Is that the amount for the accelerometer, or is that a model of the accelerometer itself?
That's the model of the accelerometer
Okay,
itself.
sorry. And then, is it going to be like completely encased in the polymer?
Yes,
Then how are you squishing it in there?
pretty much.
Okay.
Yep, it's being squished in that little cylinder.
Yeah, make sure, I know there was some issues with this, but it's really important that you have the actual accelerometer, because I'm
Mhm.
sure your CAD models like slightly off.
Yeah.
So they don't make like
Yeah.
20 of them, and then none of them.
Exactly. Yeah,
So-
and there is
Before they make.
correct. For the ones we did get with the model, there is a little bit of wiggle room. So it could be slightly bigger or slightly smaller. And still fit in the samples that we have right now. But when we do get the ones made for the actual rocket, we will give them the actual accelerometers to base the polymer pockets around.
And then if that's the case, make sure whatever possible way you put it, it's the shot, the accelerometer, that you get more.
Yeah, I don't think it's distinct, but yeah.
Well, cause I'm not like mess with the body. I'm not
Oh,
just gonna
yeah,
make
yeah.
it apart, like, you know,
Right.
make it-
Right. Gotcha.
I have two things. First, you said you're gonna like do a lot of tapping and pierce the polymers.
Yes.
How many will you get total, and like how long does it take if we destroy all of them? How long does it take to get?
It took about 3 weeks for them to make. We have 5 of them right now. So, given a month turnaround time to get more, we have a little bit of wiggle room with testing there. But yeah.
And they gave us some of the just materials that we could
Yeah,
test with.
as
too.
well.
Yeah, and two of those tests, how many? It's great that the tests are good, but for what you're trying to do with the payload, how many of those tests are actually necessary to get like controls of your experiments?
Mhm.
How much is it is the lab just having you do data collection for them?
It's not really the lab, it's more so for us. I think definitely tearing, puncturing, and like temperature are 3 big ones for us. Just to make sure that this thing isn't gonna rip inside of it shouldn't inside the payload. Or that it's not gonna become too viscous so that the vibrational dampening is nothing, or that it's not gonna become too cold and too rigid to perform correctly. What even is correct? Yes.
Less of a question and more of a note.
Mhm.
You're talking about like doing all these tests. Make sure you guys like come up with the actual testing plans.
Yeah.
I wanna know when they're happening,
Mhm.
where they're happening, how they're happening.
Yes.
That kind of stuff, so that they actually get done.
Yeah.
And probably, obviously, that's gonna happen later,
Yeah, absolutely.
but yeah, kind of like just making sure that all the tests stay relevant as
Mhm,
well.
mhm.
You had said that when you're just putting the polymer and accelerator into the cap, then you're kind of just gonna like squish it as much as possible. Standardize that as much as possible, because especially for like a polymer that isn't an exact shape, the actual effects of the dampening, I can imagine, very different based on where the geometry is. So I recommend like practicing to some capacity as much as possible to get the same best we could before.
If that's the case, I might be placed as many units actual pieces of it, so you get to work. So yeah, working to specify value.
Yeah. Get it for expect on those. Yes.
It's based on the you're doing kind of little due diligence. You mentioned that polymer behaves differently with at really cold temperatures. Do you know anything about certain temperatures? Because if rock dust and like conditions in like higher, maybe really high temperatures. So, is there anything we know about that?
Yeah, I think it said on this one, so 80 to 100 Celsius is where it starts to become more viscous, but I don't think it becomes like actually liquid until around 150 C. So
It's not any boiling.
I think it's gonna be okay. I think
Okay. The house we got was like, so,
okay,
and that's fair. That's
right? Units matter. Awesome, cool. Next slide. 15, anything before 15?
Well,
12.
Yeah.
I just, that screw switch mount looks like it might be a little bendy.
Uh-huh.
We're gonna be jamming a screwdriver in there and hunting around for it, just make sure that is held in nice and solid. Yeah.
Another comment here that if you keep that the light in the same position, it's a little bit on the side. I'd recommend like putting out not just you'll be getting this extra body so that you can see before the people are good, but you it on top.
If you could point the LED directly
At the
outward, that
window.
would be probably better,
Mm-hmm.
because it's gonna be brighter, like looking at it.
Yeah.
That would,
First, looking at the yeah.
Ben.
Do you guys mind using heat set inserts for all of the, I guess, screws that are going through 3D prints?
So all of the prints except for the mount is gonna be pretty much that heat setting too.
Brian would know this better, but there's some amount of like material you need to have on the heat set insert. I don't know if
I think I told you to have a certain.
Yeah, it's all for those ones. It's all good. All of these are good.
You'll find out if it is.
Right.
It's 3 or it is. Yeah, but.
Slide with questions. Anything on 15? 15?
So what's the concept of operation for like once you find like you walk up to the bucket, let them. Yeah, that was my question. Are you inserting an SD card during recovery?
Like
That is not what I meant when I said jump to SD when you lands.
Well, can you just do it later?
Yeah.
That is also not what I meant. That requires some additional thing of not turning off payload and like making sure that and like making sure you have code in your existing code base to like jump to that. What I meant is you have an SD card in there. It lands, it detects that it's no longer falling, and then it just writes automatically to that SD card.
that makes sense.
Yeah, because otherwise your code is way more complicated, your recovery and your like shutdown operations are way more complicated, so.
They will do that.
Yeah, that is the plan.
Yeah.
To have an SD card in there when it lands, detect landing, detect that it's no longer like moving, and then write all of the data to the SD card, save that there, and then once we get the rocket, we'll have that SD card with all the data.
And in order to show the attention, like a couple days ago, look like you can put a little cabinet on the board so the SD card can't get out. That might prevent it.
Yes.
I'm just quoting Jacob. This is I squared C, but it should be fine. What does that mean?
It's like a different data transfer thing, so everything else is SPI. This one is only S50, but it's really the same, it's almost better for sending data.
Okay, just.
It does not matter.
Okay. Like, I just want to make sure that.
Yeah.
The microcontroller has ports for
They can
both
code this.
SPI and
Alright.
Next slide, 17.
Yeah. Excel, or is each data read from the accelerometer really just one byte?
Yes, it is just something like, it's very efficient.
And then. Okay, yeah, there we go.
I had a thing on 14, I'm sorry, I forgot. Your selectable range, what are you gonna set the range of?
We were thinking, 64, either 32 or 64 at launch, and then putting it down once we did it.
You define the range when you initialize the paying code, so you have to choose one.
Okay.
And if you choose the higher range, you're losing precision. If you choose the lower range, obviously if it goes more than 8, there's max. I would. What is the maximum acceleration experience by the rocket?
What do we have in the list?
The maximum acceleration by the rocket is equal to G's.
Is what?
8.5.
Sorry, that's low ones. 15.8 G's.
That's for us, you might have like Landon or
Oh, I
Parachute or
don't-
something, maybe more.
Uh,
I think 32 is probably.
Yeah, I would say.
Yeah.
Recovery acceleration is good. We got it.
Oh.
Talk with air structures to figure out what can she do.
For-
But if you can do it lower.
True, right?
So 16, did we have any other 16 or we?
Yeah.
Yeah.
Oh, that was me doing the resolutions.
Yeah.
So, go back to the accelerometer, it's 1 byte per read.
Uh-huh.
It was on, for all 3 axes. That doesn't make sense. What was the question? The accelerator is 1 byte per microsecond.
Yeah, those were.
Yeah, no, but they said yes, and I'm just like,
Is that not?
counted like, well, because it has 3 axes, right? It'll all fit in 1 byte, it's also, yeah. That's 2 bits per. 2 bits, yeah, 2 bits.
Yeah.
That's 30.
Oh, you're right. Yeah, you can plus minus 2 that 4 string all 3. Yeah, 2 bits.
I would just double check that.
Yeah. Yeah.
I don't have this.
Hmm.
I'm not a software person.
That doesn't check out. Yeah, we will double check that. Thank you for pointing that out. Alright. 17. Someone had a question here.
Neither of these are super important, but like
Okay.
your boost converter is gonna have some efficiency and some like ratio of voltages, which changes your current a bit. You also have LEDs. You'll be fine with those, but like it's a thing that.
Yeah, make sure you're not like.
Yeah. Oh, yeah, so it doesn't blow up.
That's not not gonna be. That's kind of where it is. Like,
It will not blow up the LED.
you might need you may need to add a resistor from the.
Yeah. I have one of those in my pocket. Anyways, cool, next slide, 20, any before 21. 20.
Do we want to go back and have Mackenzie look at?
Oh, sure.
Are they showing the same things?
Yeah.
Yeah.
That'd be funny. Brilliant, okay.
Well, I'll say my comments that you're missing,
Yeah.
you're second to a self mom, doesn't it? Make sure.
Oh, yeah.
It's out all.
Yeah. Yep.
So as though it makes you can actually, you have enough connections to be.
Or
That's not about a side of all.
you're physically wiring everything.
Yeah.
Could be a lot. I would just say secure, wherever you place them in the payload. I would do like test run, of making sure when you to access each connection into connections. Stuff like that, or just stuff you don't have to fix, but. Yeah, make sure all your systems are accessible. That like first one just looks a lot worse than it actually is, so I was like, wait, that's a lot of incidents. Yeah, okay.
Good.
Yeah.
Cool. Any questions on this? Next slide for questions, 21, did someone say?
21, your cutout for measurements wiring there is directly
Yeah.
on top of the payload. Does that work?
No.
Okay.
I thought I pointed this out to air restrictions. That's okay.
Yeah.
Have you moved the cutout? Yeah.
Also, I also just realized this now. You're screwing from the inside of the payload into that bulkhead?
Yes.
I thought it was the other way.
That's true.
That's what we talked about, it wasn't the other way around.
Recommendation,
No,
Red,
outside.
tap the end, tap the payload frame plate.
Uh-huh.
And screw in from the bulkhead. You cut out parts and that's like actually possible.
Yeah. Yeah.
But also, if those happened in the CAD model, how did this end up like?
Clear code.
So right now, screws go from the inside of the payload. That's gonna be
Impossible.
and that means you need to like have the payload disassemble.
You need to put the bulkhead on before you assemble the pin.
Yeah.
Yeah.
Don't-
I-
should-
Did you put it through, but then how is it gonna connect through into the payload? You're just gonna.
Threaded holes on the payload. And then you just have a screw through the bulk.
Are you not worried about it on like?
You put some lockdown
on 4 of your.
Yeah.
Just while we're on flipping screws around, I was gonna ask about your accelerometer. Is that a screw going through the entire connecting to the lower bulkhead?
No, that's just the top. There's a cap on that holds the accelerometer, and then there's a screw from
There's
the bottom
screws
that screws
inside,
into the mount.
From the outside
Mhm.
through, okay.
Yeah.
Again, it looks like a socket at the other side.
Yeah.
Okay.
Yes.
8:15 your time, right?
Yes, it is almost 7.
You guys-
Okay,
I just want to make sure.
okay, wonderful.
95.
25? Any before then?
I guess.
Yeah.
Sorry, not 25, 29.
I got all this FEA,
Uh-huh.
where is that force coming from? Like show the calc for that.
And
Also, then more info and like views of where you're actually fixing it, where you're applying.
Yeah.
Mhm.
I can see the nice colors, but if I don't know where.
Where it's coming from, that's kind of.
you can kind of see, it's just small because you're so zoomed out. There's
Yeah.
like, if you look at the box, you can see there's.
The arrows.
You might
Show them more clearly.
Okay.
26, I think.
Yes.
You have low on your thumb on the.
Oh, yeah.
Oh,
That's
that's low, okay,
Yeah,
yeah.
that's not. So that FOS would probably be higher. 29 is
Yeah.
Yeah.
Why is payload why is electronics failing to turn on likely, and same with why is data, like how did you come up with the likelihood of all of these? Because definitely the last two on here, that should just not.
be likely.
That's a bad design if that's likely
Okay.
without getting.
I'll also say that a likelihood of 2 with a factor say of 80.
Like 8:30, you say?
You just screw books till like we.
To 10?
Yeah.
Alright. And it will probably last to 10, like there's.
Expect.
Yeah.
Your likelihoods are just severe.
We're too high.
You're also missing the textures.
Mhm.
Oh, yeah.
Oh.
That was, yeah, you need like. What you're using technical prevention.
No, they, prevention of the mitigation.
Yeah.
It's, FMEA is we call.
How
Yeah.
easy is it to capture risk before?
Okay,
So like, the LED stuff, if your LED doesn't turn on, that's a pretty low. That's a really high incentive.
Yeah.
Sometimes.
gotcha.
On air
Low detector means it's low.
on air restrictions we have it as prevention. So like how easy or difficult is it to prevent? And then that's why you have like the likelihood of
Well, the prevention is kind of that second.
but there's like a number for it. I mean
Anyway, you're talking about your bolts failing.
Yeah.
And you say like the reason we're confident that won't happen is our FOS.
Yeah.
I would also consider like the bolts could break or they could vibrate loose.
Right,
So you should also say like high FOS for them breaking, lock tight for vibration.
for vibrations, gotcha. Next slide. If any,
Is it?
30?
What's like yet again likelihood, if we don't expect temperature to be in that range of brittle or melting, why is it? Although overall, I'd like to see us, like, I'm assuming it's 1 to 5.
Yeah.
But.
Like a scale.
Have to say the scale.
Yes.
If it's 1 through 10, then a bunch of likelihoods make more sense.
Yeah.
But.
Okay, it is, what we were going on a 1 to 5 scale, so we could make note of that. Next slide, yeah, oh yeah, okay.
How many FMEA slides do you have to?
Yeah, just this. With a few more.
Not that you have to present it, but I would really just sit down and go through literally every failure mode. Because it also becomes a checklist of sorts. In your final design and final check. I did it as someone who literally just made like 200+ lines of VA.
Gotcha.
There's a lot of failure modes in it. I can tell you there's a lot more failure modes to 7, and I want you to think of them as you go through it's gonna help you design. It will help you go through actually assemble. And like I said, not the percentage, like you need a third final report.
Yes.
And it is just make you do it.
I think 20 to 30 is reasonable. Yeah.
Yeah.
I mean, hey, could you come up with 300 short? Like, once you I think once you get past 20 to 30, the arm would be like 1.
No, like, and the next more stuff is something.
Yeah.
I can do
I know you're
that. Yeah, 20 for like,
literally go advice on it.
yeah.
And see what could fail.
And like kind of what Brian was talking about, like okay, screws. How do we screw fail? Here it could vibrate out. We could go the whole thing.
Gotcha.
So
Gotcha.
feel like or like polymer. Nuts. Polymer does this. Like
does this.
and
Yeah.
then it's the capsule somehow.
Gotcha.
Something like that. Like literally just go like component by
By
component. And then look at it like integrator assembly.
Gotcha.
And to add on, like you said, you have only one thing for electronics, they fail. Literally, what's a failure mode for the battery? What's a failure mode for your accelerometer? What's a failure mode for a converter? Everything.
Wonderful.
Yes.
Cool.
Laugh at me.
Yay. Looking forward to it. Awesome. Any other questions? 34.
But you,
Depends.
No.
You should say.
Yeah. 5.5 pounds. LDS. Okay.
Did anybody? Yeah.
Has it been entered in the SDL payload comp challenge yet?
Yeah.
I don't know, it says it's done. Oh, also.
That's true. Payload, and I was like,
If the competition isn't open, has the payload been entered into it?
that would be like it's an edge of a hole.
Yeah. That's good. That'll be enterable and complete. Cool.
Looks good. Oh, seeing our post.
Heck yeah. Oh, and recording. Awesome.
Oh, yeah, I was gonna slide you. People want like a 2-minute break.
I have questions about all this. That's on.
Desert. Soil. Yo, do we think Arlo, do we think it's roots or events?
Yes.
I
I
would.
I would.
It's so funny.
Things like that. Size. And it was actually.
I won last.
Hand out right.
I'll text you.
It's my like the bus ready. Like
That's how I come to that's not gonna say.
Yeah.
Well, no, I want.
There's
I already found.
Sometimes I like to let it enjoy.
Yeah, that's what, sorry, that's what I meant, like, I will like.
I don't even read it from.
They are.
My medicine tasted good, so I didn't really
That's fine. Okay, I was gonna answer, but your diapers are second. I was gonna say.
You guys ready? I'm not gonna trip over this time.
Uh,
That's it.
it's Daniel?
Yeah. Okay, thank you. I have
You don't have context on?
No, I don't. Okay.
So you'll not be able to see people if they're raising their hands.
No, I can see if someone raises their hand. I'm just not gonna wear my glasses.
Wow.
Oh,
yeah.
Yeah. Oh, my phone's gonna die. Now that's it.
Okay.
Yeah. Okay. Aerostructures, the best sub team. Let's go. So we're gonna start with an overview. This is our con ops with correct numbers this time. Yeah, we have a what? Huh? Guys, it was late. I was tired. It's fine. Our Apple was 32,000 feet. Yeah. Cool. Moving on. This is his. Huh?
No, it always does the setup profession.
Oh, fuck yeah.
I think it was too.
There we go. Okay. This is our open rocket diagram. Couple notable changes from PDR. We went down to one centering ring, because it was excessive and making integration complicated. We have somehow bigger fins, and they're like slightly, the tip cord is shorter. Those are the most notable changes, I'm not gonna lie. Separation's right there. And you can see that very clearly here. This is what separation looks like. Yeah. This is, there were some questions and like clarification, so this is just a little bit of an overview of what we have in the rocket, before we jump into going into everything. So, nose cone eBay, and then our parachutes go in that space there. Then we have an upper camera eBay, and then the measurements eBay, then payload. Then, this long thing is the motor. We have a ballast that attaches to the lower camera eBay, and most notably, we have all of the strain gauge locations, marked, with strain gauge modules right next to them. So yeah, these are our sims. These are the simulation parameters that we use for OpenRocket and RasAero respectively. These are the general characteristics. Oops, sorry. I'll let you read numbers, I'm not reading out loud. One notable thing that we did change, the launch angle is 6 because the DTAG says I think 4 to 8, right? So we
Plus minus 2.
Oh, 6 plus minus 2. So we went with 6 as the median for that. So yeah. General kind of characteristics, we have an APO of 32,361 feet. We're going Mach 1.8 and we're going to be undergoing 15.8 Gs. 71-ish pounds. You guys can read. Oh, our stability went down, yeah. That was an issue because we were like the maximum we can have is 24. It was 25, sorry. So we're a little bit more under that than we were last time, which is good. Our minimum stability is fine. I think it's 10 is the minimum. So yeah. This is the open rocket flight scheme. I'm not gonna say much. You guys can read graphs, I trust. Razero. We got altitude, we got velocity, we got acceleration. This is the stability. Again, for those of you who've missed it in the past, like 2 design reviews, we're using Razero for stability because it simulates a 0 wind, and that's what the DTAG wants. So yeah. Yes.
Do you have a open rocket stability graph?
Not on here. I can add that. Yeah. These are our flutter calcs. The number we care about is in green because this is a complicated screen, especially to all the freshmen who are like, what the hell is this? The main takeaway is that we have an FOS of 1.79 for fin flutter, which is above required FOS of 4.5. Sick.
Yeah, that's not.
That's 1.81 Mach. Yeah. And then going into some more like dynamic stability parameters, this was in the previous design reviews, but CN alpha, these are all looking like fin stuff and stability. So CN alpha is the plot, is the slope of the plot of normal force versus angle of attack. It basically just quantifies the magnitude of the restoring force that the fins generate. And so you want a larger value of CN alpha, and the general rule of thumb is that you want CN alpha to stay above 10. So for all the Mach numbers that you're going to undergo, so we're going up to Mach 1.8, and as you can see for everything, we're above, for all our Mach numbers, we're above 10, so we're all good there. Then I'm going to throw a bunch of terms at you and throw a bunch of graphs, so get ready. The corrective moment coefficient is, we don't really care about it on its own, but it's related to like the corrective force of a rocket. What you care about is that we use it to determine the damping ratio. Similar situation for damping moment coefficient. It's about how fast the rocket stops oscillating after it's disturbed. Again, we don't really care about it on its own, but we use it to determine the damping ratio, which is a dimensionless quantity that's proportional to the rate of decay of oscillations. The optimal range for it is 0.05 to 0.3. When we look at our graph of damping ratio over time for this rocket, a lot of the time we are above 0.3. But that's better to be high than to be low. And like a higher damping ratio just means that after disturbance, the rocket is going to quickly return to being upright. And like it can cause drift, but if the rocket is able to oscillate back and forth, then the drift gets cancelled out and we're chilling. So yeah. And then the natural frequency is the rate at which something oscillates after a disturbance. So in this case, angle of attack would be the thing that oscillates. The thing that we care about is that natural frequency is different from roll rate. In general, you just don't want this number to be 1 because you want them to be different. So this is a graph of natural frequency in blue and roll rate in red. And as you can see, they're different for the whole flight. That's good. The only time they get sort of close is when we're like off the rod, which is expected. So yeah. And then these are our dynamic pressure graphs. So max Q is about 160 kilopascals. We're hitting it like 5-ish seconds in at about 5,000 feet and about 2,000 feet per second. So yeah, these are graphs up until we reach APO. But yeah.
All right, so I'll go through some of the rough material of the manufacturing plans that we've got so far. We didn't change anything about this. It's the same as PDR, but we're using SRAD tubes, not COTS. So for some of the preliminary material selections for the nose cone tip, we're going to be using 6061. I sent out a quote to Protospace. They said that they would be able to do the Von Karman nose cone shape that we have. So, and then the 6061 weighs less. which helps with the overstability. Nose cone, we're going to use fiberglass sleeve, 3 layers. The main factor going into this is radio transparency. We'll get into a little bit more about the 3 layers on a future slide. Nose cone coupler will be 3K carbon fiber layup with 5 layers. This is mainly high strength weight, and then 3K is cheaper because it doesn't have to be super stiff. Same thing for the fiber or the body tube. Boat tail is going to be 6K carbon fiber sleeve, 3 layers. This is lower in weight than it's higher in strength, and then for something like the boat tail, you want it to be stiffer because it's attached to fins, so we chose 6K for that reason. Fins, we're going to do a preliminary G10 fiberglass sheet with carbon fiber layup on top of that, 2 layers of carbon fiber on each side. This will be dependent on the shear strength test that we'll get into a little bit later. This could change to a carbon fiber core, but this is what we're going with right now because we haven't done the shear test strength. And then this is also in the FinSim closest to the material that FinSim is using, so that's why we would go with that. Nose cone eBay, PETG for customizability, PETG for strength, and then it also has some thermal resilience. iNet steel, that's DTEG. Other ones, the nose cone threaded rod is going to be aluminum for lightweight FEA. Floating charge would be vinyl tubes. I'll get into that a little bit later when we talk about the floating charges more. Upper camera eBay is going to be out of the bulk. That's the bulkhead. That's going to be
the frame, sorry.
Dependent on FEA. And then lower camera eBay is going to be made out of ABS. This is for higher thermal resilience since it's going around the motor tube. It needs to be pretty thermally resistant to the high heats of the motor. Recovery bulkhead is mainly based on FEA because we have a big force pulling on it. We went with 70-75 because it's a little stronger strength weight ratio. eBay bulkhead, also FEA determined. And then the airflow rail buttons are bought. We can't really control the Darwin plastic on that. So the rough manufacturing plans for the nose cone, we're going to use 3 layers heavy fiberglass. Like I said earlier, we need the fiberglass for radio transmission, and 3 layers for a similar thickness and weight ratio as last year, which is where a lot of our numbers densities were based off of. And then we're probably going to do something similar to last year where we 3D print a mold. We're going to do 1% infill because it doesn't need to be infilled. And in the case that we have to break it again, 1% would be easier than a higher infill. And then as for mold release, we're going to wait on composites testing and then see what we should do after that. Body tube and coupler, 503K carbon fiber. This is what we did last year, gets us the desired thickness. And then it doesn't have to be super stiff. And then these will be laid up on those size mandrels respectively. And then these are bulkhead and centering rings. Most of it is based on FEA, so we're choosing between 60-61 and 70-75 aluminum. Strength to weight ratio. If we didn't do steel because it's heavier. We're going to be water jetting all bulkhead and centering rings, and then the recovery bulkhead we cut out with the water jet, and then CNC machine for weight relief. And then the interface centering will also be in CNC machined. Both are pretty similar to the nose cone. Like I said, 6K carbon fiber sleeve. It's different than 3K. It's fairly lightweight compared to other materials that we can make it out of, and we know that it can withstand the O3400 full force for event horizon. And in this case, since we have some thrust transfer through the bulkhead as well, we know that the boat tail should survive the O3400. And then the same thing, 3D print the mold out, 1% infill that. Mold release dependent on composite testing. So we've been looking, obviously after last year, we've been looking into a lot of methods for the fin can. I've already kind of explained the fin manufacturing thing. That's going to stay the same. We're going to do the fiberglass layup and then vacuum bag or fiberglass core, carbon fiber layup, vacuum bag that, water jetting the fins out, and then seeing the airflow profile like we did last year. We're considering tacking fins using super glue. We know that when we used the heat gun to then take off the mold last year, that could have weakened the strength of the glue in there. So we're looking into different solutions for that, to make sure that bond isn't weakened, because the tacking isn't good, then it isn't good overall. And then the fillets right now we're planning to be made out of structural epoxy. We are looking in, Robbie and I watched a video by BPS Space into vacuum degassing, where he vacuum degasses the epoxy, and especially after the bubbles last year, we don't want bubbles in fillets. So we're going to try to look into methods to prevent that. We will talk. We're not going to do that on the fin can, just like right out without testing. So we'll speak to Natalie about some composite testing that maybe could help us get us more informed about that decision. Yeah.
All right, this is gonna be how everything connects and integrates. This is like important stuff. So, the airframe. The nose cone tip is connected to the nose cone eBay bulkhead via a threaded rod, and we're going to put blue Loctite on that so it stays in place, but also so that we can break it off when we need to. The nose cone is then connected to the nose cone coupler via shear pins. When we separate, the nose cone coupler goes with the body tube. So the only thing there is 3 shear pins, which we'll talk about all of those. Whatever later, yeah. Whatever. So yeah, then the nose cone coupler is connected to the body tube via bolts that also hold in the recovery bulkhead. So when we just like integrate the recovery bulkhead, we'll also be integrating in the coupler, and it's just all the same bolts that put it together. And then the body tube is connected to the fin can via the interface centering ring and bolts. Yeah. This is a little exploded view of the airframe. We'll get into more like close-up exploded views, but this is just so you can see in general all of the components that I just described apart. So I'll let you look at that for a sec. And then we're gonna move on. So more zoomed in stuff, as you can see here, the nose cone tip, it goes onto the threaded rod. In the middle here, you can see the coupler and the shear pins that go in, and then also these bolts here that I described that connect the recovery bulkhead in. We'll also put the coupler in, and then down here, you can see the interface centering ring, and then there's holes on the bottom of the body tube, on top of the fin can, that all the bolts will go in, and then one of those bolts is a rail button, and that's on the lower side of the interface centering ring, so it doesn't interfere with anything. Yeah. So then recovery. The recovery line attaches to the lower body via a U-bolt, which is attached to the recovery bulkhead, so you can see that right here. Like I said, the recovery bulkhead is radially bolted, and these bolts are also coupler retention bolts. The recovery line then attaches to the nose cone via an eye-bolt, which is threaded onto the nose cone threaded rod at the bottom side of the nose cone eBay bulkhead. The tendy is then also on the underside of the nose cone eBay bulkhead. And the D-bag is quick linked to that eye nut, and then the parachutes are quick linked to the recovery line. And then yeah, during until deployment, these parachutes are going to be inside the D-bag. So yeah. The upper camera eBay is the next component, just like moving down the rocket. It bolts to the recovery bulkhead and sits like underneath the eye bolt. And this will be bolted in before integration, so we'll bolt the U-bolt on and the upper camera eBay on. And we'll put everything in. As you can see, it bolts in from the bottom here. We should be chilling. Yeah. Next is the measurements eBay. So the measurements eBay has threaded rods that go through the eBay and connect to the measurements and payload shared bulkhead. They don't go fully through the bulkhead because then they'd be hitting and interfering. So we're gonna have blue Loctite on the threads. As you can see here, they don't come through the bulkhead all the way. And then there's cap nuts on the top. The next slide will show an exploded view, so you can see better. And then this bulkhead will be radially bolted into the rocket. So here you can see an exploded view, and also explaining for this bulkhead, the center bolts are for payload, and then the ones on the outside are for the measurements threaded rod. So nothing should interfere with each other, but yeah, this little exploded view right here. Okay. Then measurements is more than just the eBay, it's also all of the strain gauges and the wires that go into them. So throughout the entire rocket, there are holes in the centering ring, and then the lower camera eBay, the motor retention bulkhead, and the payloads and measurements bulkhead for wires to run all the way from the lower body and the fin can all the way up to the measurements eBay. Here you can just see an example of one of those little notches for wires that we have cut out. So yeah, and then once we reach up above the measurements eBay, there are also strain gauges in the nose cone, but we need to keep the, there can't be a hole in the recovery bulkhead because we need to keep a pressurized space for recovery. So instead of just having a hole in the recovery bulkhead, there is a hole for a VGA connector that will connect in from one side and the other side and like connect, and they have like a little like waterproof, like watertight connector so that that seal is held. And then the wire goes up, and then further up there's another connector that breaks upon separation. I'm sure measurements will talk about that more, but yeah, that's just to ensure that we maintain that pressure vessel. Payload. So there are bolts that connect payload. As we discussed during the payload section, we're probably going to change this because this, in hindsight, is a bit stupid. But the bolts will be like whatever. I'll probably go in through the top instead now. But one thing to note is that the measurements eBay has like 4 holes where these bolts will go so that they're not like hitting anything. I'll show that on the next slide. And then, yeah, bulkhead radially bolted. Well, this is all going to be slid in as one part during integration, so both payload and measurements will be attached to the bulkhead before we put it in the rocket. Here you can see the holes in the measurements eBay that like accommodate that, like now it would just be like the bulkhead. But yeah, so everything clears and nothing runs into each other. The motor. The motor is retained by a threaded bolt in the motor retention bulkhead that sticks out underneath, and the forward closure then threads onto the threaded rod. There's about half an inch of engagement in the forward closure and then half an inch of space. The idea is that we will put the motor into the rocket and keep turning it until it's kind of like screwed into the boat tail. And that amount of space should give us, like, we have space to turn it in, but it's secured into the boat tail and it's not stopping because it's hitting the bulkhead. We're going to have blue Loctite in the threads that connect to the forward closure to prevent rotation, but that's easily soluble with acetone and also heat, so we can actually like take it off and not ruin our motor casing. But there'll be red Loctite on the threaded rod. Oh, sorry, not the threaded rod, on the threaded bolt that goes into the motor retention bulkhead, because that never needs to come off and it shouldn't come off, so we're just going to red Loctite that. This is the like least necessary exploded view ever, but in case you were really confused, there's an exploded. Hey, it's better to have it than to not. Yeah, exactly, the most helpful exploded view you've ever seen. Okay, this is the last component, I swear, right? Yeah, this is the last component. The lower camera eBay is radially bolted into the body tube from its lower bulkhead, but the camera eBay is upside down, so what we call the lower bulkhead is really on top. Don't worry about it. It's a little, because it's referred to the lower bulkhead later. Whatever. It's going to be integrated in from the bottom of the body tube before the centering ring is put in. So we're going to integrate it from the bottom of the body tube. It's about, I think, 18.5 inches from the bottom of the body tube, so you can just put it in, your arm is longer than 18 inches, so we're fine with that. And then the centering ring is going to be put in after that and radially bolted in. Thrust transfer! I'm okay. So most of the thrust will transfer through the boat tail, which and then pass onto the interface centering ring. We're comfortable with this because although we could not run FEA on our composites, on Event Horizon, which had the same motor and similar like layers and everything for the boat tail, it received the full thrust transfer of the motor and it was fine. So we're comfortable with doing this again. But we do have motor retention bulkhead, which hopefully some of the thrust should be transferred through. It'll go through the forward closure into the motor retaining bolt, into the motor retention bulkhead, and then out to the body tubes. Yeah. Nose cone. I'm still talking. Good luck. The structure overview of our nose cone. It's a 30-inch Von Karman 5:1 nose cone. I'll talk about the 5:1 choice on the next slide just because it wasn't mentioned in PDR, so we have it now. A 6061 Von Karman nose cone tip manufactured by Protospace. This is cool. Instead of just having a conical nose cone tip like last year, they're like CNC latting it, so it'll be cool. And then a 6-inch cylindrical portion so that the couplers. A 6-inch cylindrical portion so that the coupler can slide in. A 6.008 inch outer diameter. That's including considerations for paint, so it'll be like our final OD. And then, yeah, it houses the nose cone eBay, which is going to be held in by A threaded rod secured with a nose cone tip, like I said, with blue Loctite. And yeah, you can see it on its own, and then you can also see it when it's attached with a rocket, just to like contextualize that. Why Von Karman 5-to-1? Basically it gave us the highest altitude. Like that is the short long short of it. There's multiple studies that have been done on all the different kinds of nose cone shapes, and in general Von Karman is considered one of the best. Paraseries is also good, but just running it on sims of our rocket, these numbers are from like a previous version, but they still stand. We got the highest number with 5-to-1 Von Karman, so we went with that. The nose cone eBay. The nose cone eBay is has a 3D printed PETG sled. It houses 5 batteries, an Easy Mini, Siren, TeleGPS, Alvin Beacon, and a Blue Raven and a breakout board. It has 5 screw switches all in a line, and there'll be screenshots on the next slide where I'll explain where everything is. 5 screw switches and houses antennas. It sits on a 6061 aluminum bulkhead, which has 2 4-socket terminal blocks, and then on the other side, underside, it has the Tendi and the eye bolt. Here's some more screenshots. So, okay. This is Siren. This is the TeleGPS. This is what?
That was the easy.
Sorry,
that was Elvin.
Sorry, this is Elvin Beacon. This is the TeleGPS. My bad. Siren, Elvin, TeleGPS. This is the Blue Raven and its breakout board. The holes for the wires that come out of the battery, and then these holders are just cable management stuff. Then we have 5 screw switches all in a row. It's really nice. It's just like 5 holes just down the nose cone. It'll be great. We'll label them. And then this is the Siren antenna. It has like a little holder. The antenna is going to be hot glued to the holder, and then the holder is attached to the sled. And then this is the TeleGPS. No? Sorry, that's the Easy Mini. It's been a long day. That's the Easy Mini. And then also you can see our beautiful giant clocking notch. I'll explain that in a second. Oh, Brian. Brian's gonna make a guest appearance for 1 slide. Talk about the wiring diagram. 2 slides, my bad, 2 slides.
Can we get some gameplay?
All right. He asked for it. So, hi, I'm Brian. This is the wiring diagram for the eBay. You'll notice the flight computers used in this setup are the Blue Raven and Siren S1R3. We have the Easy Mini, Alvin Beacon, and TeleGPS hooked up to their own battery and screw switch there. You'll note that on Siren, this is not the wiring diagram that has flown on any rockets. This is instead more accurate of what might a Blue Raven be like without a breakout board. I'll get to that later in the avionics section, but that's that. I'll just leave it sitting for like 2 seconds because Daniel seems to be into it.
Sorry, I was trying to find ground.
Those 3 lines mean, Daniel? What do those 3 lines mean?
It was also asked to make a wiring diagram with Siren not as your secondary flight computer, instead using an Easy Mini. Do that, you'll know everything is the exact same, except there is an Easy Mini hooked up to some wires now. That will be all. Thank you very much.
Okay. The nose cone eBay bulkhead. This is where I'm going to answer all your clocking notch questions. So, it's a 6061 aluminum bulkhead. It's 1/4 inch. It houses 2 4-circuit terminal blocks with 3D printed covers on the underside, the Tendi Descendi, an eye nut rated to 1,800 pounds, and then E-matches will go through the bulkheads to connect to floating charges on the other side, and then a clocking notch. The reason the clocking notch is so big is because it is also a, like, do you remember how I said there are, like, holes for measurements wires to go through? There's also these giant strain gauge modules for that like house the like computers for the strain gauges. So we have, it's fine. We have 2 in the nose cone. We need to get the eBay over those when we integrate it. So we needed a hole in the bulkhead. We said we might as well just also make that the clocking notch. Because that's the spacing that we had. So, as you can see, it'll line up. It'll go over the 2 strain gauge modules and then up to our clocking notch, and there's a billion tapers everywhere to make it really easy to put in. So yeah, You can also see some weight relief on the bottom there. Just because FEA weight relief. Yay.
I was gonna say the tendy also is not in the way there. It might look like
Oh,
it
yeah.
a little bit. It's not. I had like a vertical view in CAD when I was doing it, and it was.
Trust
It's
it.
not
Trust it's fine.
Yeah.
Yeah. It's not going to be in the way.
We thought about it.
we thought about that.
Yes.
Okay. Let's come eBay bulkhead FEA and thread shear. The force from the drogue is about 140 pounds, and that gives us a minimum FOS of 2.1, which is the arrows.
The tendy bulkheads.
Oh, tendy.
That's where the tendy mounts, which is where the drogue forces apply.
Yeah. And then we did a bunch of bolt, threaded rod shear, and tendy bolt shear, and FOS is all fine. 30, 160, 4.5 for the iNet rating. Yeah.
All right. So now to get into a little bit of the recovery. So here's the rough recovery scheme. What? Oh, Mitchell. Okay, so we got on the very right. Actually, that's your left. On the very end, we've got it at launch. There's going to be a D-bag up on the top. Rockets all assembled. We hit apogee. Boom! It breaks. That's the nose coming out of it. Oh no! I guess I should have said separate. The shear pins break. And then that's the drogue. And then once it hits 1,500 feet, tendy will pop out. Release. I'm using really bad terms, but the tendy will activate, popping out the main parachute. And then it'll descend to a slow speed on the ground, and it won't come down fast. Here's the rough packing scheme of the D-bag. So we've got on your left side, we've got the main parachute, and then on the right, we've got the drogue parachute. You can see tendy up there. All the shock cord attached. We got quick link right there that'll release when that's gonna be attached to the drogue. That'll come out at Apo. Yeah, everything connects to an iNet bag. Yeah. So this is the drogue. We're using a 25-inch ellipsoidal parachute. The CD for this, we were not able to get the drop test done. I'll talk a little bit about the drop test later. So these are just CDs based on the descent rate of Event Horizon. So you got some numbers here. I won't read them out to you, but Robbie already went through drogue deployment for us, 140. The max velocity under drogue is right after it deploys the 164 feet per second, which is 1 foot per second below the D-type requirement. So yeah, it's not that for most. Sorry, I should have prefaced with this. That's only for like a second. Like once it comes down after that, it comes down to around 100 feet per second. Oh, and yeah, this is why the drogue had a big force, was the horizontal velocity of drogue deployment. Authorized arrow is around 200 feet per second, horizontally. So, and then here's the main parachute. It's going to be a 76-inch toroidal parachute. The coefficient of drag for this is going to be 1.84. This is what I was saying about the descent rate. It's not going to be 164 feet per second. Once it gets down to a steady rate, it'll be at about 96 feet per second. And then when the main deploys, it'll release a force of 1,100 pounds. And then that should let it float down to the ground at 27.3 feet per second. It's going to be made out of ultra low porosity nylon fabric. And then the lines will be made out of 1/8 inch 725 Spectrum microline. Max drift, this is worst case, I guess. Worst case in terms of parachute deploying. Main at Apo, it's going to drift pretty far, but nominal deployment, it should only be about 3 miles away. So here's some of the line lengths. The drogue to main is going to be 66 inches. Drogue to our body is going to be 101. The main parachute to eBay is going to be 128, giving us a total length of 295 inches. The minimum clearance here is 18 inches. And then what we're going to be using for this is 3/8 inch tubular Kevlar. This 3,600 pound force, or pounds of like tensile strength, is given by Wildman. We did some strength testing, and our testing numbers were pretty similar, so we're willing to accept that. And then we're using shock factor of 2. We did some research online and with the Rocket Discord. And shock factor of 2 was based on, because it's not technically an instantaneous inflation, because there is time in between. Shock factor of 2 is in fact worst case. It's not best case. Because there is that like time that it takes to inflate. So it's not an instantaneous force. That way shock factor. That's why we chose the shock factor of 2. And then the ends of recovery lines will be sewn. That max load, I'll talk about more when we get to the testing part, but that's how we got the 3,200 pound force that I was able to take. And then the parachute mounts will be knotted at, and the max load for that is 1,800 pounds. So here's the ejection. This is mainly about E-matches because, or not E-matches, the floating charges because that's a new thing. So we have the E-matches, which are the little red lines, will extend from the nose cone bulkhead. And then these little the black tips over here are vinyl tubing. They're 2 E-matches in case one of them fails. Shear pins, right? They're really tiny because we're using number 2 nylon shear pin. Number 2 nylon shear pins. So they're pretty tiny, but they are there. We're using 3 of them. E-matches ignited apogee, breaking the shear pins, causing separation. And then the floating charges, when we're integrating, since they're 2 to 3 feet long, they can kind of like hang outside and away from the person. So in the worst case scenario that it does blow up, it won't be right on your hand. And yeah, so that should be better for the safety of whichever one of us is the one that's integrating that, so we don't get our hand blown. Oh, or Arlo. Yeah. Okay. Well, then Arlo's hands will thank us when he's integrating this. So here's the recovery bulkhead. This houses the U-bolt for the recovery lines to attach to, and then also underneath that U-bolt is the upper camera eBay from earlier. Robbie touched on this a little bit. The weight relief only goes partially through the bulkhead, like it doesn't go fully through because of the pressure vessel thing. I'm not going to talk about the VGA cable. Karthik will talk about that. Right, Karthik? Yeah. So here's the recovery bulkhead and bolt shear. This is so the recovery bulkhead obviously experiences a lot of force when the main deploys. So this is making sure that the radial bolts don't shear. So we've got all the calculations here. We're above the 2.0 factor safety that is required of us. This, I believe, actually, other than I'll talk about this later, but this is the lowest FOS that we have on the rocket so far. I just won't talk about it. No, actually, I have to talk about it now. I changed the U-bolt material from what it was at like PDR because found out that we were actually under the FOS rating, but there was an exact same U-bolt with a different type of steel, so we had to change the steel for that sake. Oh, and then a little note: the 3/8 of like depth of that was picked for max engagement of the threads.
And both going to be in handcuffs.
And handcuffs.
Yeah,
that did that. Yeah. So this was the shear pin determination to see what size shear pin we needed. It ended up not really mattering because when I did the drag separation, we were in compression for the entire time. So we see the total drag force. That I should put max, but the max drag force was 230. And then that's split up between the upper and lower section. And then the normal force at joint there, 4.44, is positive, which means it's in compression. So they are like pushing together, which means that in theory the rocket should not separate. We're still going to have shear pins on there just for safety's sake, but the factor of safety on this isn't really applicable because our calculations show us that it's in compression, so we don't need them. But yeah, we chose 3 number 2 nylon shear pins just in case. So here's an exploded view of the shear pins. They go in the rocket. It's the steps.
Like, go to that.
Oh, so yeah, so Robbie's saying there's steps, so they break, come out, boom, separation, breakage. Yeah. Sorry. Anyway, black powder calcs. So the recovery, like the spaces in between the measure or the upper camera eBay and the like top bulkhead is going to be 320 inches cubed. Of that, there's going to be 157 inches cubed of occupied volume by all the different components in there, mainly the D-bag. The adjusted volume is just that minus that. And then we know that we need 210 pound force to break the 3-256 nylon shear pins with a factor safety of 3 because we still need factor safety for this. And this leads to a primary charge of 2 grams and a backup charge of 2.5 grams. And then we have the inner diameter and lengths of the vinyl tubing that we'll use. So this is recovery research plan. It's the same picture as last time, except some of them are green now. So we did our most recent iteration of shock factor determination was done on Tuesday. I believe the next slide will talk about that. So yeah, last Tuesday, a week ago, not today. Toroidal parachute drop test. If any of you guys have been keeping up with that, that's been a pain in the butt. Has not happened yet, but we're still planning to do it. Hopefully that should give us more accurate estimates of the CDs of all the parachutes and stuff, because the current CDs are estimates based on Event Horizon landing data, which doesn't really factor in the CD of Event Horizon itself. And then on the very left there, we have the charge wells and the ejection testing. So right now we've done the preliminary design. We have the I just went over the whole design for the ejection charges, floating charges. So next thing that we're going to do is an isolated charge test. We'll set up a test charge outside of rocket, see how that goes. And then because we have the upper camera eBay, we want to do a camera shield test to see, one, if the upper camera eBay can withstand the force of the ejection charge going off. And then also to see if there's a bunch of debris that's clouding up any of the footage that the camera is going to get. Because if it's just going to be covered, even if it survives, it's just going to be covered by a bunch of debris. There's not a whole bunch of point for that. So we'll do that, and then full ejection testing. We'll do that. That was going to happen anyway. And then here's the Kevlar research that we did. So we know that this was all done with the 3/8 inch tubular Kevlar, which the 3,600 pound force was listed on Wildman. So an ultimate strength for the line ends was 1,200 pound force. For the parachute mounts, this was around 1,800. And then for the knotted ultimate strength, this is where we got the 3,200, which was similar to the ultimate strength that Wildman lists. And then for the parachute mounts, it was actually way up there. It was scary when we were doing it because it was approaching the max that the machine could do. But it was over 5,000 force, or 5,000 pound force in some cases.
I'm a little stupid. Those are backwards. The knotted are the numbers on top. The silver are the numbers on bottom.
That makes more sense. The labels. You should not it. I think it's.
So the quick link applies to the sewn threads. This is like a worst case scenario if the lower body comes down and the nose kind of pulls up on the quick link and drogue. The drogue can pull on a quick link on a sewn end. So we're not going to use the 500 pound force of sewn end for that. We'll use a knot for that. And then so I will preface by saying the parachute mounts right now have factor safety of 1.6 because we couldn't do the drop test, and then also we just did the testing on Tuesday, and then Arlo got hit by a mean sickness, and then also it was Thanksgiving break. We are thinking about workarounds for that so we can get that above 2, but that's what it is for right now. So yeah, I'm thinking about that. Body tube, pretty much the same as last time. It'll still house all the same things. We're still planning on using the aerodynamic rail buttons. Pretty much everything's ready to be bolted now. Oh yeah, coupler stays with this part after separation. So here's a picture of kind of how everything is connecting in there. So the coupler starts at the very top there. Body tube then starts halfway down the coupler. We have the strain gauge modules on the side there. Screw switch holes for the measurements eBay. And then the coupler ends where that close to the end of the measurements eBay. Then it's kind of like one picture going down on 2 sides. Over here, that's measurements eBay at the top. Then you get the payload with the screw switch holes. Go down below that, motor, thrust transfer bulkhead, and then some strain gauge modules underneath that. And then this is kind of a continuation of the last slide. Below that thrust transfer bulkhead, you've got the lower camber eBay radially bolted in. There are screw switches below that with LEDs attached to them so that we can see when it's on. Centering ring, pretty self-explanatory. And then the interface centering ring is below that. This is to make sure that the rail buttons aren't gonna break when it's sitting on the launch rail. All the factor safeties are good, so yeah. And then this is the handcuffs for the motor retaining bolt, making sure the threads don't shear. Yeah, so the expected load, that's from thrust curve, it's gonna experience a max of around 1,067 pounds force. The shear force is calculated for a 3/8 inch, 16 threads per inch steel rod. The factor safety of that should be fine. And then, so that's thread shearing. We got a factor safety of 7.7 for thread shearing. And then the tensile force, actually it should be compression. I saw Garrett's not on that. But we're also showing in terms of compression force. And also buckling shouldn't really be an issue since it's only, it's like a 1/2 inch, right? It's sticking in between the motor and the door chamfer. So there's like a 1/2 inch, so buckling shouldn't really be an issue there. This is for bolt tear out and bearings. Bearing stress, you can see for the tubes, because it's carbon fiber, bolt tear out's pretty good. Same thing for bearing stress. This is the max force that it can occupy. And then this is all done with in terms of the max force that was applied, which is the main deploying. So as long as it can survive main deploy, it can survive everything else, no matter where it is on the rocket. These are the pressure port. These are pressure ports. Maximum launch temperature is going to be 115 degrees. Maximum velocity is that. So those are the factors that went into this calculation. We're going to have 4 of them on the nose cone around the eBay. And then the minimum diameter of this is going to be 3/16 of an inch. Recovery section is going to have 3. These are going to be 1/16 of an inch. And then the lower body is going to have also 3, 64ths of an inch. Yeah, and then the ones that have the asterisks on them already have screw switches in them, so they can act as pressure ports a little bit. So yeah. Here's a picture of our pressure ports. So here's payload measurements. Payload measurements will be attached to single bulkhead. Robbie mentioned, easy to integrate, should just slide in as one piece, and then you can just radially bolt those in. Here is all the factor of safeties for the different portions of the rocket flight, which will experience force, so you can through the thrust. Probably not going to break out for the thrust, probably not going to break out for the drag and the parachute. And then the ground hit factor of safety. Yeah. So this is the setup for the FEA that we did on the measurements and the payload bulkhead. Yeah, I'll just let you guys look at that for a second. And then we have the results on the next slide. You can see the minimum factor safeties are 11 and 6.5 respectively. And then so here's going to be this bulkhead shear calculation. I guess I can walk through some of the numbers. This is bolt shear at the max acceleration, which is going to be the 15 Gs that are happening, and then you have the factor safety at the main deploy, and then same thing for the bulkhead shear. Like you don't want the bulkhead to shear either. The bolts won't, the bulkheads won't. So yeah, and then here's a picture of the like a side view of the bulkhead where a screw's going in. Yeah. Motor retention. This slide kind of got covered already a little bit earlier, but threaded rod into the motor retention bulkhead that'll stick out underneath, and then the forward closure of the motor threads onto this from underneath. Blue Loctite, dissolvable, we'll clean it really well. Red Loctite on the top, that doesn't need to change. Yeah. And then here's the bolt shear and motor retention bulkhead PA. Yeah, we're within the factor safety for all of them. Yeah.
Okay, so now it's time to talk about the 2 camera eBays. So we have 2 camera eBays in this rocket, 5 cameras total, 2 in the upper, 3 in the lower.
One of them has to, right?
One of them has to work. That's what I'm saying. So yeah, the upper camera eBay is up there, the lower camera is down there. We talked about that. So for the upper camera eBay, it features 2 flight tested in Brian's L2 SQ11 cameras that'll be looking up. So the idea is that we'll be able to see separation and deployment and all that cool stuff. It's got 2 18650 batteries and 2 boost converters. And it's made of a 6061 aluminum frame plate, and then a polycarbonate cover. What I say, guys. So here you can see it inside the light tube, it on its own, and then the exploded view of how everything connects together. Alex kind of touched on this already, but we're gonna test this eBay. We can either do it during normal ejection testing, or if we want to test it earlier, we can just test with like a spare CF tube. Composites has 1 million of them, and a piece of polycarbonate, just to see how the ejection charges are gonna affect the plate. That should be fine with the 6061 frame because that's aluminum, it's fine. But we want to test it with polycarb. And if you go to the presentation, you can see full written up plans with like intro and methodology. They're very nice. Thank you, Ryan. Yeah. The lower camera eBay is made of kind of 3 main components. So this is the upper bulkhead, but like I mentioned, the eBay is upside down, so the upper bulkhead is actually really on the bottom. Don't worry about it. It houses the screw switches, and then bolts into the main compartment of the lower camera eBay. The screw switch mounts are adjustable, so we can move them up and down a little bit. If we mess up the holes, it's fine. And then they also hold an LED, so that like they'll be like you'll be able to hear if the fans are on, but also you'll be able to see it because once there's like 3 fans on, you don't know which one's which. So there's 3 LEDs. And then the lower bulkhead attaches the lower camera eBay to the airframe. This is what's radially bolted in. It also is able to mount a ballast, and how it holds the brackets for holding the motor tube that goes through the center of the lower camera eBay. So you can see the FEA, minimum FOS of 11, so we're chilling. And then this is the main compartment. It houses 3 like sets of electronics, and in each set there is a run cam thumb with an 18650, a fan with a 16340, and 2 boost converters. And the cameras are turned on with a button, so they can be turned on before integration, and then the screw switches are to turn on the fans. So yeah, one big concern that was brought up is the lower camera eBay is wrapped around the motor, and the motor gets really hot. So these are like, we did the math, but Ryan did the math for the heat transfer rates for the motor softening the plastic. Here you can see the assumptions that we make to do the math. So the motor reaches a maximum legal temperature of 220 degrees Celsius, and let's say it sustains it for the entire flight. The conductive heat transfer will occur through the fiberglass insulator, that's that motor tube in the center. The plastic is the only source of thermal mass, and the initial chamber temperature is 55 degrees Celsius, and ABS deflects at 98. Again, the full math is attached, but the calculated lifetime is 6 minutes, which is longer than our entire flight, which is 5.4 minutes. So yeah. And then here you can see like all of the numbers. I'll just give you a second to look at it, but we're good with reaching the heat deflection temperature. Cool. And then this is the battery and memory capacity of the camera eBays. The main takeaway is that we're fine. The memory is completely fine, like 46 hours, 15 hours, like that's really chill. The runtime, the lowest runtime we have is 9 hours, so that's really our restriction. The really good thing to note is that the fan for the lower camera eBay runs longer than the cameras will, so that's never going to be an issue. Cool. Okay, fin can. This is the fin can and how it attaches, so we kind of went over this. But the interface centering ring connects the body tube to the fin can. The fin can has a 6-inch cylindrical section and then a 12-inch conical section. 5.867 inch floor diameter, 4.1 inch aft diameter, and a 0.1 inch wall thickness. And then the O34 has a 4-inch diameter lip on the end that overlaps on the boat tail, so it like stops before it goes through the boat tail. This is like one of the more notable strain gauge placements, is that there's going to be strain gauges on the fins themselves. So there's going to be 4 in total. I just showed you 1 because otherwise the diagram would get confusing. But there's going to be 2 strain gauges on 2 different fins, so 4 total. The wires from those strain gauges are going to go into a small hole that's going to get drilled into the boat tail and then connect to strain gauge modules that are housed inside of the boat tail. The strain gauges are going to be like obviously glued to the fins, and then the wires and everything will be covered in a small amount of epoxy just to keep everything secure. And then the hole itself is going to be plugged up with epoxy. It's going to be a tiny hole, like composites strength wise, everything should be fine there. So, yeah. And then the interface centering ring. The fin can transmits force through the centering ring directly into the body tube, and so the aluminium lip, there's like a small lip that like the fin can and the body tube like hits it. It's put into compression, so either the fin can or the body tube would have to buckle for this to fail, but we did FEA anyway, and it has been an FOS of 33, so we're chilling with the interface centering ring. One other thing to note about the interface centering ring, it's really thick, so like we have that clearance, but there's like a bunch of weight relief around it, so it's like not that heavy.
All right, so the shear modulus determination of the fins. If you aren't up to date, this is a new defect requirement this year. So the required for plan testing. So we're going to use the Instron, the same one that we used in the recovery line testing. This is in Rob's lab, and it is capable of going up to 27 kilonewtons in tension. And then for 0.3 inch thick specimen breaking force is going to be that 25.2 kilonewtons. And this is assuming the COTS carbon fiber reinforced plastic material properties. And then yeah, so what we need to have is 5 to 10 samples of the carbon fiber fiberglass plate to 40% of fracture. We still have, if you look in the like back part of the bay, we still have the like sheet from last year, so we can just cut out from that and use those. Some other things that might be nice to have would be 5 to 10 samples of carbon fiber in the center and test that to fracture. Elevated temperature test would be nice, and then also a tensile and modulus fracture test on chosen material. And then here's the machining plan. We have our stock from McMaster, so we started practicing some of these external threads, but we need one clamping block, which is just one operation on the CNC to make all 4 of them. And then for the main block, we need 5 operations total, 1 to cut the L-shaped profile and drill holes, and then 1 on each, so that's like 2 total to carve out the pocket, and then 1 on each, so also 2 to drill holes for the 114 tap. That'll be manually done. And then the adapter is shown over here. We have to manually turn that on the lathe and cut threads. That's what we've been practicing for. So yeah, that needs to be done. And then once that's done, we just need to set up a date with Rob, and then we can pull. Oh, I guess actually also we need to cut out the coupons, but once we have all that, we can pull and determine the shear modulus for the fins. So now we're going to get into low launch. This is a low launch coupler. It's going to act as like a spacer because the M1939 is smaller, not radially, but like it's shorter than the other one. So we need this in order to fill up that gap. So what's going to happen here? Thrust is going to come up through here. It's going to transfer into this bulkhead, which is going to go through the coupler up into the thrust transfer bulkhead. We're going to source the coupler from Wild, and we're not going to buy some, or we're not going to make some. We don't have to. And then the threaded rods here are all secured with Loctite, red Loctite for the most. You know what Loctite is? You do what Loctite for this? Oh no, fine. You do? Okay. Just making sure. The launch coupler, bulkhead, FEA. We've got a new max force because the thrust of this motor is a lot less. So you can see all of our factory safeties are above the 2 requirement, especially the motor retention one. So, yeah. Oh, this is what I was saying. This is what I'm about to say about the Loctite. So this is how it's all going to connect to make sure that nothing unthreads. We've got red Loctite on the top, which will stay there. For also, like we're going to obviously have the same thrust transfer bulkhead, so that's why we can use red Loctite up there. Also red Loctite on the threaded rods into the coupler because those don't have to move. And then red Loctite on the bottom as well. The only thing that we actually have to get rid of is the motor casing because we'll have to take that apart and clean it. But that's the only part that we use blue Loctite. So. Oh, you're right. Yeah. That bolt too, because if that didn't come off, then we wouldn't be able to put the big one on. Here's a drogue overview for this one. It's also a 25-inch sort of parachute. Velocity of drogue deployment is 168 feet per second. Drogue deployment force 194 pound forces or pound force. And then the maximum velocity under this drogue is 114 feet per second. It's made out of the same ultra low porosity nylon fabric. And yeah, this is the horizontal velocity at drogue deployment. Here's the main parachute, the 78-inch Toyota parachute, propulsion drag 1.8. This is the descent rate with the drogue at main deployment, 92.5 feet per second. The main deployment force is 1,050, and then the touchdown velocity is going to be 26.6 feet per second. Here's the same max drift if the main ejects at apogee. It's going to go about 3.3 miles, and then if it works correctly, it'll go about 1.5. Here are simulation inputs for RISE-Aero Open Rocket. This is based on the launch site in Ohio. So, and then we did 60 degrees because it seems like a reasonable assumption for temperature. We won't know how to, we won't know the temperature day of until we get. But I'll give you guys another second. So here are the characteristics of the low launch. We're going to go about 14,000 feet high. We'll go Mach 1 exactly. And then we're going to pull about 8.5 Gs.
It's like 0.998. So the same.
It rounds to 0.1 or 1.
I'm going to say 1 because
Go ahead.
yeah, 1. We're going to break sound. Yeah, so we got maximum stability 23.2 and then an off-road stability of 15.9. This rocket's going to be a little lighter because we don't have as big of a motor and a lot less propellant as well. Yeah. Here's the flight scheme. This is going to be, again, a bunch of graphs. I'll probably just skip, tell you what it says, and then let you look at it for 10 seconds. Here is the RISE-Aero altitude, 14,000 feet. Yeah. Velocity, feet per second. Acceleration. 30. Dynamic pressure. Fin floater. Hopefully our fins don't flutter on the low launch. That would suck. And here's the compliance matrices. These are just the general requirements that we're talking about. So the vehicle shall have two 15 rail buttons. It does. And then all the eye bolts shall be closed eye forge type. It is. This is just for the camera eBay. It's not using any of those batteries, so that's good. Housing requirements. All energetic devices, arming features. That's about the floating charges. So that's why we started the floating charges because of that requirement. Vehicles shall implement completely independent and redundant recovery systems. Yes, I'll have multiple. I'll go into ones that have numbers since you guys can read the other ones. But for each independently recovered section, that should be a compartment with 2 inches to 4 inches of clearance greater than the space required for the recovery equipment. Currently, the space in between the recovery and the bottom, or the U-bolt, is 2.5 inches. Yeah, and then this is about the flight waiver of low launch. We are going under 2,000 feet of the TMO flight waiver, so we shouldn't run into any issues there. And yeah. So withstanding the loads, any coupler and the two inside the rocket will extend at least one body caliper. R1 coupler does that. Coupler not intended to separate shall be affixed by mechanical fasteners and a permanent adhesive. It is factor safety of all load bearing components should be above 2. This is the 2.04 that I was mentioning earlier. That's minimum. The rail buttons shall be capable of supporting the launch's fully loaded weight. These were the really big factor safeties that were talked about during the rail button bolt shear thing. Yeah, vehicle shall be constructed to withstand the operating stresses determined by simulation and retain structural integrity. That was what a lot of this was about, all the FBA stuff. Gordon's telling me to wrap it up. I'll just speak to it. You guys can read it. Both of these are pretty self-explanatory.
Right. And then this is the FMEA. You can see the full FMEA, but we're just gonna split them for flip pay. we have a scale of 1 to 5. So for severity and occurrence, that is like least severe to most severe, or least likely to occur to most. And for prevention, it's easiest to hardest to prevent. So yeah, I'm just gonna highlight the main important ones, and then you can read through the rest. If the floating charges fail to ignite, we don't separate, become non-ballistic, that's bad. We're gonna do ejection testing, and then that won't happen. If the recovery lines, I'm just gonna go through like the red ones. If the recovery lines break, that's also bad. So we've been strength testing them, and then we're gonna do analysis on deployment testing to like make sure we have active deployment forces and things like that. That's like very involved, but if we do all of that, we will make sure that that doesn't happen. All of this is like pretty chill. It's basically just like ensure we pack recovery properly, do ejection testing, and run simulations and do FEA is the main gist of everything here. The big red thing here is fin flutter and divergence. If we have fin flutter, that will be bad. We saw it happen with Helios. The only thing that we can really do for this, like not in terms of like proper manufacturing, because that's not really what FMEA is about, is doing FinSim analysis. And FinSim is not the best tool, but it's also the only tool that we have. We're hoping that we will get more accurate simulations by measuring our shear modulus and being able to like actually put in a custom material into FinSim. So that's the best that we've got for that, and hopefully that will mean that fin flutter doesn't happen. So yeah, that's it, structure.
Let's take 5 minutes to stretch your legs since it's been like an hour. We'll try to get over that. You gotta tackle it over. Brian, over. I tell you, oh, Brian, that looks great. I like the lips. I haven't even like surgery. Take a look. I was just like, I put it together. She fucking whatever. I was like, or yeah, like what? Is that way you organize that? Somebody.
Wait.
Oh, he did not.
Hey, we're working 360. Yeah.
What's your?
Maybe next night.
It was nighttime. The only exotic way
Like in a car.
Just make sure that
Yeah, single lot. I probably should. You're driving like the entire time, so you can't.
What it would mean.
Who's responsible for this?
Oh, you can go out. Yeah.
The officer.
They say we have their
Is it the officer?
Well, that's what actually said.
I was gonna say.
I feel like not.
I feel like.
You open the thing, nothing's like the view.
Hey, Arlo, what's my number around? I mean,
What's 72?
oh, why are you wearing glasses?
By the way, the only reason I don't care is because you're really bad. I always would have like this kind of but then when I started wearing contacts, my prescriptions are different. So I always like
This war, I was concerned. I was like, wait, I need this. It's a combination of.
No, I'm actually saying this. But I'm not like this side. I know.
I have dyslexia, so I do this.
Yeah, just 10 more seconds,
Just
by the
spend.
Okay, let's. Great. Can you go back?
Oh, I see.
Okay, can we take our seats? Take a bed call.
I'm actually gonna.
We're still.
That's all we expect.
We're still missing for you to.
They're still doing it.
Okay, friends, and whatever the rest of you all.
Countrymen.
Let's start this thing.
Romans?
Yeah.
Oh, yeah.
Roman singular.
Okay, so here's the measurements. I know Aerostructures has talked about this a lot, so here's our own spiel. So first, we want to go over our eBay assembly. This basically houses almost all the components used for data collection and data analysis. So I'll just leave this up here for a couple of seconds just for you to read. And then here, just more views, different angles of what our eBay looks like. Okay, so then here I just wanted to explain like a really general overview of how our data gets from our strain gauge to our Arduino. So from the strain gauge, we get resistance data because the strain gauge is just basically a variable resistor. That goes to the strain gauge board, or so also referred to as module sometimes. Then that resistance data gets converted into an analog voltage data, which gets sent to an ADC or an analog to digital converter. As the name suggests, that converts that into a digital voltage data. Just one thing that it doesn't necessarily manipulate the data itself, but there is a level shifter between the ADC and the Arduino. Just we're taking the voltage from it from a 5 volt signal to a 3.3 volt signal. And then it gets to Arduino, and then the Arduino takes data and puts it into an external flash for its data storage. Okay, so now I'll be going over the CAD of all the module holders. So just to start off, I'm going to go from top to bottom, like physically in the rocket. And the way these module holders work is this is the module, and it'll just slide in, and we'll just glue it onto this bottom surface here. So these two are the nose cone module holders. They do look really similar to each other, but in the next slide, to show just because of the way since the nose cone is curved, the modules do have to be slightly different from each other based on its vertical distance. So these are like the precise distances from the very bottom of the nose cone and then between each other where they should be placed. And then, as Ravi mentioned, these strain gauges or these module holders will be clocked to the notch in the in the eBay bulkhead, just for easier integration. And then our way of attaching these will probably mark these locations like inside the nose cone and then know where to epoxy these module holders. Okay, and then the next couple slides is going to be like CAD of all the module holders that are, I swear they are different from each other. You just can't see it very well. So this is what the module holder looks like for the coupler, which is just, and here's the body tube. So just the surface is conformed to has a just larger diameter. Here is a little weird one. So this is the boat tail module holder. The reason why it's cut off like that is because this part here will be attached to the straight section of the boat tail. And since the boat tail starts to slant inwards, the holder itself cannot extend forward, otherwise it goes through the material. So it'd be like hanging. But there's still plenty of surface area inside the module for inside the holder for the module to be super glued to. And then in a similar way, so since we're having strain gauges in the boat tail and on the fins, we decided to have another ADC in the boat tail, and just so that it can be easier wire management when we're wiring from the boat tail to our main eBay. And so the ADC holder will follow like a similar design as the module holder, in that it'll be hanging just so that it doesn't go into the slanting portion of the boat tail. All right, so then here is the material selection for all of our manufactured components. So we're aiming to just be able to 3D print all of our components. Most of it will be PETG, just because it's good 3D printing material for pretty good 3D printing. Sorry, and then the two special ones would be the components that go in the boat tail. So since this is in close proximity to the motor, we wanted to use a material that has a higher heat resistance. That's why we're going with ABF, but they're also 3D printed. Okay, so then here, go over the strain gauge locations. They have changed since PDR. So the big thing now is we're going to be putting strain gauges on the fins. By the way, this open rocket, this is the correct open rocket model. It's just rotated 45 degrees, just to show that we're putting strain gauges on fins that are orthogonal to each other. So we 2 strain gauges on each fin, and then we also want to put strain gauges on the boat tail itself, just because that's where we expect most of the thrust transfer to occur. So we can measure the deformation. And then we have strain gauges in the middle, just because it's also close to the thrust transfer bulkhead, but we also might expect the largest bending moment to be in the center of the rocket. Then, all right, this strain gauge is here will be on the coupler, just since it's a different material, or just a different tube, just want to measure the deformation of that. Also, like when it, during separation, there might be a forces experience. Well, there will be forces experience there. So on a similar note, the other 2 strain gauges here will be on the recovery bulkhead itself. Again, just so you can measure forces coming from separation. Then finally, we have 2 strain gauges that we right below the eBay bulkhead, and that's just to measure strain on the nose cone, which is a different material, so fiberglass. And then I basically go over all those points on this slide here. Okay, so then here is we're going to go over integration. So as mentioned, so I'll start top to bottom. So as mentioned before, we'll have the strain gauges in the nose cone be clocked to the notch in the eBay bulkhead for integration. And then most of these, since we're going to be so since the camera bulkhead will be going through the bottom of the main body tube, a lot of these strain gauges can be affixed like in Cleveland, just because some of those bulkheads will be more permanently affixed. And then of course, and also since the boat tail is a separate piece, the ADC and the strain gauges and their modules can also be attached in Cleveland. So we're hoping that a lot of the, apart from just the connections itself, everything can be put into the rocket before heading to the comet. And then just like one more detailed overview of these steps that we're thinking of for integration for each part. So especially big thing would be the strain gauges that go in the boat tail, especially for the fins. As Aerostructures mentioned, we will be drilling holes into the boat tail just to fit the wires in. There was some concern about the wire length for the strain gauges that come pre-attached to the modules that we buy. So what we decided what we decided to do is we actually, through a sponsorship, got a bunch of strain gauges from Micro Measurements. These strain gauges have come with a much longer wire. So the plan would be to desolder the strain gauges that come with some of the modules that we buy, and then attach the Micro Measurements strain gauges just so that we can get that extra wire length, and so we can put it through the hole and attach it to the fins. And then for all the other locations, we'll be using the strain gauges that come with the modules. So it's that. And then nose cone. The nose cone is the main thing is just integrating the VGA cable. So we'll be splitting the VGA cable here in Cleveland, and then we'll also be attaching the holder for the VGA cable onto the bulkheads, which we will go into detail in a later slide. Okay, so forget. I guess
Is your form hazing me?
Sorry?
Are you hazing me right now?
Yeah,
Hazing is not allowed.
Unofficially.
Officially modules?
Yes.
Okay. This is like the fun, like exploding part, where we get the data from the top of the rocket to the bottom of the rocket where our like processors actually are. So we're cutting this hole in the bulkhead, and then to save pressure a little bit, we're gonna buy this like special VGA like waterproof gasket. And then we're gonna screw it in from the top of the bulkhead to keep like a little bit of a seal in there. And then we're taking the screws out of the VGA cable, so the connection is a pretty loose fit, but hopefully not so loose that it will come undone, you know, before after. That's all.
Cool. Thank you.
Just like the emoji.
Yeah. It wasn't me. It hated me.
Okay, so then here is to show, okay, what are we gonna do with this data? There's a lot of math on here, but basically what we're trying to do is we're measuring a strain gauge, and we'll get that into voltage data. So to get from voltage to a strain, we'll use something called a gauge factor, which is just basically a coefficient given to every single strain gauge. So for example, the strain gauges that are already pre-attached to the strain gauge modules has a gauge factor of around 2 to 2.2. From getting the strain, we can calculate stress through a Young's modulus. Young's modulus can be experimentally determined in Rob's lab. So whenever we get the tubes, we can experimentally determine that Young's modulus, just so that we know what that is when we do the calculations. And then from stress, we can calculate a force. So then we can know at each point what the force is looking like. Okay, then we'll go over a wiring diagram, and I will bring Ian up.
All right. So this is the full wiring diagram. So I'll go into a bit more detail on each one, but like the overview is that the microcontroller, the Arduino that's controlling everything, and then we've got the two flash boards that we're going to be writing to, and then like two main sections with our two separate analog to digital converters. So this is just the Arduino, and also like our power supply management. So we're going to have 4 batteries, 2 of them in series in parallel, and then Karthik will go over the battery calculations with capacity and everything, and then passing that into a buck converter to get it down to 5 volts, and then also a screw switch there so we can turn it on the pad. So that's going to serve as, well, one thing that's kind of weird is that some of our components work on 5 volts and our Arduino works on 3.3 volts. So the 5 volt right there serves as a 5 volt power supply for our 5 volt components, as well as power supply directly into the Arduino. And then those are labels that are part of the SPI and stuff. So these are the 2 flash boards. We don't know exactly what boards they're going to be at the moment, but the idea that one of them is going to be like the one we're writing on in flight, and then we're going to have a second hopefully larger one that can store redundant data. So like backing it up initially, backing it up after land, just to make sure we don't ever lose any important data. And then those are going off of, oh, one thing I forgot, I should have mentioned earlier is that we actually had 2 SPI lines that we're going to be working on. One of them is exclusively for the 2 flash modules. The other one is exclusively for the analog to digital converters. And I'll talk a bit more about that in the programming section. So, and then, so this is for the fin strain gauges. So you see we have 6 strain gauge modules, as Karthik mentioned, and then our analog to digital converter here. And then these are the level shifters. So that converts the 5-volt output from the analog to digital converter into 3.3-volt signals that Arduino can understand. So just the SPI things, and then also one line that indicates when it is ready, just kind of like an implementation detail. And then this is for the body strain gauges, so everything that is not the fins. We're gonna have 8 of those, and Karthik wanted me to mention that some of these wires are gonna need shielding, specifically the analog ones, is that right?
Yeah.
Yeah, so the analog ones shielding as much as we can to prevent like any data loss or like inconsistencies or noise from the vibrations.
From vibrations, and also just from, since we're in close proximity to the nose cone eBay, in case the radio transmissions interfere with our data. Okay, so here are battery calculations. So these numbers, the main thing that changed is, main 2 things that have changed is the amount of strain gauges. So now we're up to 14 now, and also we have two ADCs. So we get a total capacity of 7,875 milliamp hours. We're still going to go with our plan of using 4 18650 batteries, and I'll explain in this slide. So the idea is we'll have, try to best explain it. So we have 2 pairs of batteries in series with each other, and then each of those pairs we put into parallel. So after all that, we would have a voltage of 7.4 volts and around 7,000 milliamp hours capacity. Once that is put into a buck converter, and with this assumption of an 80% efficiency, we get a total capacity of 8,288 milliamp hours, which puts us above the required 7,875 explained before. And then
So for a bit of how the software is going to work, one important note is that our microcontroller has 2 cores. So the one core is going to be used for just collecting data from both of the analog digital converters, and then also our chip has an onboard accelerometer that uses I2C. So I still haven't worked out the timing with that, but hopefully the first core should also be collecting accelerometer data, and then the second core is going to be dedicated to serializing all the data to the flash. So the initial stages is like when it boots up, it's going to copy the data. Like if there's any important data on the first flash, like it's going to copy that to the second one, just to make sure we don't accidentally lose any data ever. And then it's going to clear the first flash and then start recording the strain data into a circular buffer, and then using the accelerometer data, wait until it detects launch. And then when it detects launch, it's going to go into the second stage, where it's just recording all the data from the strain gauges in the accelerometer and sending packets over to the second core that then serialize. And then it's also going to be detecting whether or not we've landed. And then after it detects landing, it's going to again copy the data from the first flash to the second flash, so we have it in 2 locations.
All right, now I'll move on to FMEA. So here it is. I mean, biggest thing is of concern is just fasteners and adhesives, like physically fasteners and adhesives coming out, especially since we're relying on a lot of epoxy to keep our strain gauges and their modules hold it. So one of the big things, so with fasteners, using like Loctite just to further secure it, and then for areas that we're using epoxy, just maximizing the surface area between points of contact, which is what we strove to do in our designs. Other things are things that we assume would occur during flight or during integration, just because a lot of things will be moving around it. So solder's getting damaged, or data corruption occurring, which data corruption we can mitigate by adding the shielded wires I mentioned before. Strain gauge is not being calibrated properly is an issue in regards to the Wheatstone bridge, just making sure that both sides are balanced. It's controlled by a potentiometer on the board itself. The main way we can mitigate that is just by covering the board, which is what our strain gauge module holders look like. It's a full coverage over it. And then bugging code, I mean, this can be mitigated just through a lot of testing done on the ground here in the next semester. And then batteries running out, just making sure that we bring in the regular equipment. Okay, then compliance matrix, not much has changed in terms of here. I mean, since we added a lot more components, the amount of hours has decreased, but it's still above the 14 hours set in SRR. And everything else should remain the same. Thank you.
Okay, avionics. So we're gonna go over Siren updates, testing updates, and then the requirements and risk matrices. Okay, so Siren updates. We got Siren R3, new GPS, new flash, magnetometer, and fixed the E-match traces, so it's able to launch E-matches now. But there is bug with the barometer. There was an issue with the GPS traces, which I fixed with solder, but the solder is fragile, so we'll have to figure that out. The E-match pins need to be wired differently because they don't have enough current to blow it on their own. And then there's an issue with the power management system on Siren. It wasn't able to handle reverse polarity. So the buck converter exploded. General Siren announcement, do be careful plugging in Sirens from now on. Check the polarity 3 times because we're running out.
And also, if you plug it in and it starts getting really hot, please unplug it.
Yeah. Common sense, I guess. I don't know. But yeah, we fixed software, GPS traces. Be careful with batteries. And these are the changes for S2 or S2 R1. We're gonna add power pins for the E-match like on the Blue Raven. We're gonna fix the GPS traces. We're gonna integrate LoRa onto the main board. We're gonna downgrade the MCU because it doesn't need to be as good as it is. We're gonna move to the GPS to the front center of the board, MCU to the back. It's just a better layout for like reception and noise issues. Fix the power issues. Add an LED or something to tell if the E-match is closed and make Siren black, obviously. And then software progress, everything's done. The magnetometer, we need to figure out why it's only returning 1 value, and the common filter is a work in progress, but it's actually getting there. So it's, we'll go into that later. And yeah, here is the conditions of flight. You gotta power the nose cone eBay file. That's the one that runs the code for the nose cone eBay. And then the conditions for flight, it needs to pass 10 G acceleration, 5 of 10 meters. There's a 30-second time lock for apogee to make it not detect early. All that, and then mainnet 1500. Okay. And here's flowcharts for all that. So this is the main function. It will receive the packets, flight data, flight modes, and broadcast data every 0.5 seconds. And then these are the different flight modes. You've got standby, check if the conditions for flight are met. If so, we'll go to flight mode, which will check for the conditions for apogee and deploy apo and main if the conditions are met. Landed, pretty self-explanatory. And then You got testing.
So we did 7 major tests of Siren over the past month. I'll just go through what each of these are, how we did them, the results from them, and analysis of any further data. With GPS Fix, we restarted the GPS traces so that the GPS is fully functional, and tried to get a fix in the ThinkBox parking lot. And there were also various fixes that happened at various other locations that we weren't trying to, which is good. We have the Kalman filter, which is far enough now that we can get results on it, actually. We tested its ability to analyze Siren's actual position via angular velocity combined with other data from the Kalman filter. We had E-match firing, in which I took my L2 eBay, wired it up to simulate like an actual eBay, and proceeded to attempt to fire E-matches on that. We have long range radio, which so far has occurred in 2 rounds. The first was here at ThinkBox and the Quad, in which we tested Siren's ability to transmit radio inside of Helios's nose cone from up to 750 feet across various different modes of we had line of sight through foliage and no line of sight at all. Other tests, we had data logging, in which we just tried to simulate a flight and collect data from that. The throw test, which is my personal favorite, I'll get into that. No, I'll get into that right now. We took Siren, we wrapped it up in a bunch of foam, and we threw it as high as we could to see if they could detect apogee. We have a cool video of that later on. And the avionics test flight, which, well, we put it on a rocket and we made it go up. More about that later. First, here is a video of the Kalman filter in action, measuring Siren's orientation live as we rotate it. This is based off so far this is based off the initial reference of Siren when we turn it on. For like a later global orientation, we will need, I believe, the complete Kalman filter be done, but it will be possible. So that's that, just wiggling around, pretty cool. This is the throw test. This is one of the attempts we did. Yeah. I should note the green light is when it detects apogee. So for that, it was pretty much instantaneous. If I could hit the pause button, there we go. Oh, slowly, yeah, right about there. I would say that's a couple inches before apogee, which is great. So on to the beneficial results from these tests. GPS Fix was successfully obtained in the ThinkBox parking lot with accurate 3D data. E-matches were successfully fired both in the eBay alone and in an actual integrated rocket. Long-range radio, we've had complete success with line of sight up to 0.75 miles, through foliage up to 750 feet, and through various no line of sight, also around 750 feet, which is good. Data logging, we get accurate data all the time, exactly what we want. Kalman filter, still a work in progress, but we are getting good results with accurate orientations within certain error bounds. Throw tests, we found the error of apogee detections to be about a meter in the worst case, but again, closer to inches in like a general parabolic trajectory. And the avionics test flight, the beneficial results of that were we can survive a rocket's ascent and descent much faster than we wanted to, accurately detect apogee at the correct locations, and send the signal to close an E-match circuit. Now onto some more unflattering results. The GPS traces, as previously mentioned, are incredibly fragile. As of right now, I believe that most, if not all of them, will need to be resoldered. This is not a permanent issue, but it is time consuming, and we are going to try putting hot glue or other things on there to provide more structural support that can actually survive a flight. For the E-matches, it did not work in the wiring as we intended. We had hoped that we could connect E-matches to Siren's pins itself to fire E-matches, but we cannot provide enough current for that. So we are going to have to most likely do the alternate wiring scheme in which these are powered directly via battery. Again, not like straight to battery controlled by a screw switch, so we can actually like safely do that, but it's looking not pleasant. And for long range radio, for some reason, we could not get any packets at all up to 3 miles away, which was the furthest distance I tested. This is most likely just due to an antenna mismatch that happened during the test, but the Minnesota weather was very uncooperative, and we will not be able to test again at such distances without considerable planning in Cleveland or waiting until winter break again. As for data logging, there were 3 minor issues. One, magnetometer data is locked at a set value for some reason. All data points are double counted, and we are getting data that we do not actually want from other flights. But it's good because we are getting all the data from the flights that we want. So it's not really detrimental to anything we're doing right now. It's just something quality of life we can fix. The throw test, as I mentioned before, apogee detection varies anytime between this is a bit off, a few inches before apogee and up to a meter after. It's up to a meter after more often when we're throwing it perfectly vertical for some physics reasons I do not fully understand. But given that this is probably not going to be the case in flight, it's very precise for our uses. And I didn't put you put on there?
Yeah. I can talk about the common filter. It basically, in order to get the result that we had, Serena multiplied by 1.5, just like everything. So it's consistently underestimating for some reason, but that was like the first preliminary test of the common filter. So I think for the state that it's at, that's a pretty good result and easily fixable.
I said before, no, Chris said before, science is just inventing constants to make it work. So it's to the test flight. Initially, there were 4 test flights planned. 2 of them flew. 1 of them was supposed to be an observer. 3 were supposed to be firing charges. The one that flew was on Chris's L2. Unfortunately, we did not get any usable data from that because 1, the barometer bug told us we were 5,500 feet underground, and 2, the acceleration threshold was not changed from Helios, which both of those issues are now fixed and will be good for the other 2. For the 3 flights that did plan to use Siren for firing charges, only 1 of these flew. Arlos did not go due to a design change. Mine did not go because of a last-minute hardware issue where the MOSFETs were fried from a buck converter explosion, which was only discovered during ejection testing. But for the actual dedicated avionics test flight, we did not have any of these issues, and we were able to fly. Many things went wrong with this flight. To start off, radio and GPS were not tested at all because due to the time constraints that we had on the field, there was literally no time to set up that. And then, when we hit apogee, neither E-matches from Siren nor the Blue Raven fired or ignited, so the rocket came down ballistic at 282 feet per second. The rocket was destroyed. Blue Raven... Oh, I made an error on this. This was with the Raven 4, not the Blue Raven. The Raven 4 was destroyed. Siren, however, was able to be recovered, and we did get flight data off of this, from which we saw the correct apogee detection and the correct main detection had there been a main parachute. We do not know exactly what went wrong with this flight. We are on it due to no documentation of the exact wiring beforehand or tests of continuity whatsoever. We do not know if this was a hardware issue on Siren's fault or an issue with the wiring of the eBay. I can 100% confirm it's not a software issue because Siren only logs an apogee detection after it actually sends the signal to the MOSFETs to close the circuit on the E-matches, so we know that that was detected and the circuit was closed. If we could from actually brings me to my second issue, we do not know if the MOSFETs actually closed the circuit. We do not know if the circuit was actually closed had the MOSFETs worked. This is again due to various things. As 1, we did not completely test the continuity of the flight or of the circuit beforehand, and 2, the MOSFETs currently have no way of knowing whether the circuit is closed, only whether they would have closed it. A continuity check might be possible to add on this iteration of Siren. Again, it will involve some wiring on the backside, as I will show you later in a second, but it is possible. And on this flight also, we used this bad wiring scheme that I talked about way back on the eBay wiring diagram, in which we had it connected to Siren's pins instead of to battery power, which in order to reduce any failure modes, we are going to not be doing that because just to be sure that Siren will work. But this new iteration, it's this new orientation, it's not anything bad. It's just the same way that a Raven would have without a breakout board. So this is the exact wiring scheme I was talking about. We've manually taken power and put it straight through Siren's pins. This is taken straight after the avionics test flight. You see pin 18 and 20 are to ground, and then pins 14 and 16 were set up to have power that the E-matches would run out of. This did prove functional in all of our ground testing, and these solder joints are still intact and have a continuous circuit post-flight. But again, we're not going to be using this scheme because, one, it introduces the possibility of more errors as a trade-off for convenience, which was a pretty bad idea. But given this data, I would like to express my opinion that Siren functions near completely. Going on to requirements. The only thing, these are all unchanged. The only thing up in the air is 1.1.0-5. Arguably, this is debatable. We had it simulated. We had it successfully blow E-matches in flight conditions, not in flight. Up in the air on that, up to you guys. And one issue we just made here is that we did not get a reliable GPS fix in flight conditions because the soldering issues again. We have reliable fix now, given that we fixed it, but it has not been tested on an actual rocket. These are all unchanged relating to eBay wiring and GPS transmission. And these are all unchanged relating to the composition of the eBay.
Okay. And lastly, the risk matrix. So it's all pretty simple. Main thing is the E-match joints fail connections, which would result in the failure of all secondary ejection charges. Obviously very bad. But pretty much everything else has a pretty low likelihood besides the GPS fix, which has a low consequence because that's not flight critical. And then also this one, sample rate in sync with vibration of the rocket, would be pretty unlucky. So not a huge issue. That's it.
Let's take till 8:50 and we'll start back up again. Wake up.
No, you can't look at the shit he's doing, so it doesn't say. As long as you have the link to the part of it. Yes. Yes, it was a lot. Oh my god. I've never had moon stuff before, so we have risk matrices and just like talked about like when to show Eve and then no, so
I'm playing. That means how we do this at the same time.
Can I have you help me figure out how to?
I do.
All of the FMEA that is doing the front. It needs to be fully input. Like we don't.
So yeah, we
Don't do that.
You gotta go somewhere.
What?
You guys, how do you evaluate all the numbers?
This was the recovery test.
Which we evaluate with newer value, and then multiply it.
God, haven't we focused some plans or something?
Oh, it was like. It was like that, but it was basically.
I'm not, I don't care that much.
Have like that kind of. It was like.
Guys,
Why are you like this?
guys.
Yes, but it's going on Arlo. What happened? Huh?
I'll see you tomorrow. So my name's on this one.
In your name.
Good.
Come on, Joshua.
Something's broken.
Are you leaving?
Something's broken.
Remy, is it broken?
Remy, say
What?
say things. I found the option. It's not the same. Walk around the meeting. Wait, Roman, am I taking a break too?
I think that's it.
You know,
We don't need to do.
You wanna wait after?
What?
You wanna first shit after that?
Like it's.
Yeah.
Alright, after.
I don't know, they changed it after I finished the cat.
I thought it was funny. I was just like Roger.
Me? I didn't know if it's because you need all the holes to be the right.
I was like, he was like.
Wait, I'm sorry, it totally should be.
It's not, there's cuts that don't go all the way in.
There's no three-dimensional. Which. I thought.
This was after everybody. I stayed back to San Jose.
So I stopped at the whole day, I went, and then I was like, I'm sorry, I want some.
Guys,
So I don't actually.
That was like Costco. This was. I was standing there.
I know.
All went.
Well,
And I stayed back. To
That's what I'm thinking.
It was just me broke on mine.
I had in the nose cone assembly.
Just all loose wires.
Yeah.
Just all loose wires.
Right?
Oh, yeah.
Anybody upload this?
I'm recording a Zoom meeting, so no.
I
like could help, but I won't.
Those 30s, and I'm about to unplug it. I'm about to unplug it, I'm going back and then just sit back on his feet, but it has all of my notes from this. So. It's
fine. Kind of heavy.
I know one's bad, Mackenzie's group is good.
They have.
Was that before she learned about it?
No, it was the way that it happened.
I didn't have time to
Actually, so it doesn't happen. Anything else was that was. And then two.
I know
you're you don't know design yet. You design presentation.
I don't know what it was like before I got yeah,
That's horrible.
I don't.
I pulled all 9 of those LPs 3 months ago.
You have 2 people that do work.
I don't think I know what it does.
It's that.
We like Stalin.
It's not.
I think I.
That.
That you
I think that was.
So then like, there would be no reason why we wouldn't have a ballot.
Yeah.
You optimize it.
No, even like.
It's a. I think it's like it's one bite.
Oh, yeah.
Is that
It's one bite.
Four bites instead of one bite, and then we have.
buffers.
No, well, it's 12 times as much as we do. No. What's the
Like, I'm officially surprised.
Because you're only gonna start storing data.
She didn't like ever step up to do this. And I was like.
It's only some of them are gonna be active with like the code.
Like, better. She's a good.
I just know that like for our we had to all of the time was spent like hyping on the tab.
I swear, all the way. But anyway, like she's now a good.
Well,
and also like
some guy or something on a rectangle which is surrounded by. Are you?
Okay, take your seats, please. Yeah, fuck you, Disney.
What is this guy doing? We're yapping about our design.
Where's the other airship?
Back there.
Oh, okay. Just wanted to confirm.
Hey, all of my leads know when they're taking notes, right? Okay. Right, Jacob? Okay. We're gonna go back to air structures.
What slide is that?
Ooh, you were on 200.
No,
36.
That's the title slide.
36.
I think a lot of them.
Keep on.
3. Nope.
Oh.
No,
Sorry, I'm just kidding.
Yeah.
Yeah. Okay. A couple of things before we start this. First of all, if you have any stylistic, like, oh, this slide looks bad, please just write that on the slideshow, leave a comment. We don't need to waste people's time on that. Second of all, please be nice. Everyone who's up here has worked a lot on these things. So criticism is great, but constructive criticism, please. And then third thing, if there are things that we are just going back and forth about, we are going to table those things so we don't spend 10 minutes having a discussion in front of everybody. Sounds good? Great. What's our first slide now?
58, we've already talked about 6. I have 43.
I have 39. I think the diameter there at the very front is that for like the nose cone versus the.
Oh yeah, the nose cone's wider than the bodysuit. Sorry. Okay. You said 43?
Yeah. How do you set the launch rail?
There's a launch rail calculator in a spreadsheet that it's like based on like where the top rail button is relative to the top of the rocket, and yeah, it's in a spreadsheet.
What motor exit diameter did you use in that zone?
It's 2.54. But yeah, whichever one you said.
Oh, cool.
Are these focusing with no wind? In both of these?
No, for like the thing that the DTAC cares about is stability from RAS Aero. RAS Aero simulates with no wind. However, we also want to be able to simulate with wind. Yeah. What? Huh?
We have a wind speed.
Oh. No, but it simulates with. I don't know. They want whatever RAS Aero says. They said that in the town hall. So.
I would just confirm.
I'll
because
confirm
you talked about like no wind.
Yeah, I'll confirm that.
So
Maybe it doesn't. Or maybe it's the very. I'll confirm that.
it might be stability off the rod or something. Yeah, but just one.
Yeah. Okay. Next slide.
50.
50.
I just wanted to look at this for a bit more.
Oh, that's okay.
Where do you get that 9K feet from?
It's altitude at Midland is 3K, and then max Q / max velocity occurs at around 6k. 6 + 3 is 9.
Did you update, is how does you calculate, is it from?
It's from CAD.
And then is the thin material set as the worst case or?
We got rid of carbon fiber reinforced thermoplastic because thermoplastic is different enough to the point where it's not pertinent to what that is. So technically, I think you asked about this last time. That we didn't use that. This is the next worst case after that, and this is applicable carbon fiber reinforced.
It's the worst case thermoset, right?
Yes.
Okay, so this says alpha of 0 to 4 degrees. This different from your launch angle because the launch angle is 6, which is outside that range.
Yeah, alpha. It's like the. Sorry, I'm talking. Angle of attack.
We're going this way.
Okay.
56.
56.
I don't think that X is. The higher damping ratio doesn't necessarily mean that the rocket's gonna like do that quickly. It just means that the oscillations are damped much more.
The time in between each oscillation is the same because that's frequency dependent.
Yeah.
But the time it takes for it to decay is less because it damps.
Yeah.
So
yeah.
Yeah. There's two ways to interpret it, but
Yeah,
the way
I guess it's
interpret
two different positions.
yeah, I think it's
Okay.
I get what you're saying.
Yeah,
Never mind,
15.
I get it.
No, I get 59.
Do you use this in any place other than FinSim?
No, don't think so. Cool. Next slide.
62.
62.
You say 60, 61 goes less than what?
Oh, then
Steel.
70, 75.
No.
Not steel. We can't use steel.
But
Yeah.
weighs-
Sorry, yeah.
It weighs less than steel.
It-
It's about the same.
It can't be steel now.
Yeah.
It weighs less than 70, 75. And like it weighed less than. Sorry, I'm explaining.
Yeah, when you get a,
Sorry.
when you get a brass.
I'm explaining badly. Yeah, it is the like weighs the least than like what is like reasonable. Yeah.
Couplers do also take on like a decent force. So is there like justification? You mentioned like when you were speaking, like that it's like those two layers are gonna be the exact same. I'm assuming, right?
Pretty much it.
So that's fine. Like we're not gonna reinforce the couplers in any other way, or like you think they're strong enough?
They're strong enough.
And
I
it's
mean, we
based
weren't
on-
planning on.
and this is based on what, just like prior.
This is based off of what we've done in the past. Honestly, we don't have much better stuff to go off of.
Because I would say, well, actually, you might. But like when we did the event price, for example, like, you're basing a lot of the stuff. Like, okay, like, that's fine. We did that internal layup on the couplers.
Right.
That actually I think was great.
Yeah.
For the sake of the couplers. So I don't know if that's a consideration you guys wanted to have, but
I will say Helios had a higher stress flight profile,
Yeah.
and while it did not work, the couplers did. It was the fin that failed. So it went past max Q with this type of design.
Yeah, that was more the reasoning.
Yeah.
Okay.
Did you have something?
I was just gonna say like the thing that considers also sanding. Me got to a layer on.
Yeah.
Yeah.
Your thing is.
in which case there's sand body tube instead of
Yeah.
You kind of go over this later, but as 3 layers feels low for the Bocal, no big word for that horizon, but you are also going to drill some holes in it for the strain gauges.
Like
as well, they are small, yes. However,
We drilled pressure bore holes in the event horizon one of a similar size.
Yeah, it's shown.
Thanks.
I trust. And we know well the one other thing that I didn't like mention, but it was on the slides. testing like the only other kind of test we have to go off of is we tested 6 layers of 6K last year, and that maxed out the Instron machine and was able to handle the force of an O55. An O55 is greater, and so like basically like it's kind of just like hand wavy, but like that's something, and so I trust that 3K being half like will be fine for the force of an O34. But yeah, you something?
Like the material used for the, I guess, whatever tip to tip layup you do, over the weekend, would that be included? Is that included here, or is that something?
Oh, it's gonna be 6K, and then I guess we didn't include that, yeah.
I
But
guess-
it's gonna be 6K. We'll probably do 2 layers, maybe 3.
There was I wasn't involved with this last year, but I think freshman year there were additional pieces of CF like in different kinds of layers.
Right, they'll be
Feel that-
Talk about that during.
yeah, but real quick, there'll probably be like 2 on the fillets and then 2 full tip to tips. Yeah, and then varied directions. Cool.
Next slide. Okay, I know you go into a lot more detail about the ABS later, but I don't know if it was explicitly stated. The ABS over the PETG, because the PETG does not have those properties for the front stuff. Is that correct?
It has some, but it's not to the same extent that ABS. It's ABS.
So
is
PETG would not be accepted, but ABS is.
I mean, we haven't done the math of PETG, but ABS, like the ABS choice initially was because of higher thermal resilience, and given that it's at 6 minutes, I wouldn't be comfortable going lower than that. So ABS works.
Okay. Also, is it 63?
Yes.
Airflow real buttons are probably fine, but I would say double check the D-tag anyway. He's sending that away.
Oh, sorry.
I think people have had them at,
Yeah, but it does change year to year
Oh, that's true.
because someone does something and that goes wrong. That
Okay.
changes the rules. So since the updated D-tag is out, just check that they don't say, "Hey, you can't do that."
Also, just messaging.
Yeah. Hey, can we do?
Maybe just give a read through for
Yeah.
that idea applies to everything.
Okay.
Next slide. This seems very similar to last year. Are you using the same band rules and all? Is
Yep.
that- Okay.
That was a bit.
And then for the notice note, it sounds like it's the same thing as last year, but it's 3 layers, so it's at minimum 3 layers of the section when there's overlap of 4. Is that correct?
Yeah.
Okay.
For the 1% from Bill, Birmingham had brought up an issue, if you're vacuum bagging and shrink tubing, there's gonna be like or something, but. Do you, the Intel might have.
Do you guys vacuum bag?
We don't vacuum bag from this code. We do vacuum bag the
Hotels
well actually we should we shouldn't
So I don't-
vacuum
we're not
bag.
vacuum bagging anymore.
The only 3D print that ever gets put in a vacuum bag is the 2 holders on the end of the thingies, and that we don't care about the infill for that because we're not breaking it.
Okay, yes.
Cool. Next slide.
70 degrees.
I have 65.
60. Okay.
I just wanted to make sure, because there was changes to, eBay bulkhead.
Yes.
Is that-
Oh, that's not reflected here. Sorry, we changed the eBay bulkhead very last minute. The eBay bulkhead will now also have to be CNC because it has some weight relief on it. So. Yeah.
That is, like, if we care that much about weight relief, is there a reason it's still 60, 61?
It ended up being lighter. Like it was 70-75 and it wasn't good enough, so then we increased the thickness, but it ended up working out with weight the best to have it 60-61 and thicker than 70-75 and thinner. Just with the FEA.
My greatest.
Okay.
CBF.
Yeah, sure.
Just a general statistical, a couple times, do we have a sum total on how many plots you can CNC in the pocket?
Not off the top of my
I
head.
can
I think
basically
it's
guarantee
around-
you it's less than last year.
Yeah,
it's coming around like 6-ish.
I mean, like.
Can we talk about that during our?
Yeah. Cool. Next slide.
73.
67.
7.
Just do the testing we talked about earlier today. The vacuum gas stuff.
Yeah, if we choose to do that, I'll make sure Natalie and Composites does some form of testing on that matter.
Cool.
You mentioned the issue with super glue. I think we talked about this.
I think it's
The conclusion we came to is that like your thing strength is not coming off your tacking and how strong your tacking is, it's about the surface and your villains.
Yeah.
So I don't need to worry about like the structural part of the city.
Yeah, I think we probably want to go with super glue because it when we did tacking last year, super glue was easier. I think you're right. It doesn't matter. Next slide.
69.
Next.
Would you also want to put Loctite under the eyeball, like on the underside of the eBay wall?
Yeah.
Sure.
73.
The threaded rod to the iron.
Sorry, yeah.
I think that we usually red Loctite though.
Oh.
Okay. Yeah.
I think I asked this last time, but just to double check, this is recording the parachute. This isn't recording the outside.
Yes.
Okay.
This with the
Washers.
On. Oh.
Oh. Bars.
I mean, if you probably could go and just have them get sides. It doesn't look like the space.
The actual FEA was done with washers. That might be an old screenshot.
Yeah, let's do that. Cool.
Oh, is that you both also spec the D type of comments that?
Yeah.
Um,
We looked a lot into the U-bolt. Next slide.
Oh, so just the. I wrote, how are you ensuring about the potential, the one permanent connection with the threaded rod? So the threaded rod go like halfway through.
I believe it's 0.3 inches through a 0.375 inch bulkhead.
Is the hole tapped all the way through and you're just not gonna install the last like 2 threads?
Yeah. Yeah.
Okay.
And okay, just give us a with. Okay.
You could also just put it on a flat surface and sleeve it and it stops.
Yeah. Whatever works. Well, it needs to be a certain height with the cat nuts.
Yeah.
Yeah.
Julian made a note on the eBay design for the last design review that the screw switch might not be close enough to the like body tube. I don't know if that would be the case here.
It's a bit far. You could reprint the cover to just have a bigger cone or just print spacers. Okay. So they're pretty easy, but you should do one.
Okay.
Next line. What's the distance between that hole and the gap? Like measurements, like in that guide. Looks like
I have to move anyway.
What?
The
Oh.
measurements guide, the whole.
Was that me?
Oh. It's fine.
Okay.
Is it?
Sorry. He touched something and the thing's fine. No. I'm talking about this. Huh? Oh.
Is this
Sorry.
thing rotated by 45 degrees anyway for the payload?
Well, the payload's gonna have to move.
Yeah.
TLDR payload's gonna have to move. So we'll just put them. We'll rotate the payload 45 degrees. But sorry, what was your question? I was distracted by that.
The measurements gap.
Yes.
There's a threaded, I'm assuming threaded rod hole, yeah, right next to it.
Yeah.
How close is that? Are you worried about tear out?
Not off the top of my head, but we have done FEA. Right, it was fine.
Yeah, well, it's the FEA is fine. But we're gonna have to move the notch, not payload, because if payload's rotated 45, then it hits the I guess it's fine actually because the
Oh, wait, no.
I think
through
there's
it.
one just move the bulkhead, because if you rotate payload also you have to move
Yeah.
screw your like location.
Okay.
So just rotate the bulkhead. I would just recommend moving that notch and having it. That
Well, then we gotta move
the
it,
big
yeah.
center. And it's
Yeah,
just
like
like
not to be slightly off.
Yeah.
I'm worried about.
And also the concern, like you said, FEA is fine, which is good.
Yeah.
The concern is less structural and more just manufacturing.
That's true.
When you actually drill it,
Okay.
it's just some. Yeah.
We can just move all the notches over and hope.
You can. Yeah.
Okay, next slide.
79 now. Just you have the like inserts into the or like the cavities in the measurements eBay and the bottom of it. Make sure that you update those when you update.
Yeah.
The
Yep. Cool.
85.
I have something from Gordon Brady.
Mhm.
When you're threading in, it should be good with Loctite, but he brought it up. I can't fully explain it, but when you like threading in the motor, you're like, you could have the like threads of the actual bolt that you're threading onto, like, come out just because of the force of the body. Like if you're going to work, like until it stops, it could, like, the bolt could come out. At least that's how I think he was saying.
Saying the
With-
red lock.
with red loctite?
Yeah, it has to go start
Yeah,
spinning
back.
around. Yeah, I think he was saying he did put back out. So, I
Okay.
think you're good with red Loctite, but I would talk with him just.
If you wanna make it more robust, the way you do is make an outline for a hex and then insert like a little silver metal tapping screw in, that's kind of.
I don't know.
That makes sense.
I think you're.
I think that's fine, Tim.
We really don't torque the shit
Yeah.
out of it.
Okay.
This is more to do with integration, but I'm talking about motor. The O34 has some kind of specific tooling, if I recall correctly, it's right in here.
Yeah.
Have you look into that?
I don't know what this
It's
wrench
been
is
on-
about, guys. I googled it. I don't know what.
Message.
Message in the Discord, you
Okay.
need to figure it out, because I remember someone had to like.
Yeah, I
I
tried googling it and it said.
to a message.
Oh, did you? Maybe I missed that. Okay.
You might have to Discord in the every Discord. ask
Yeah,
them the Loctite
every
test
Discord,
or-
every yeah.
Yeah.
Mhm. Cool. Okay.
So.
We'll figure that out.
Uh,
Next slide.
83.
83.
I said this in the previous one, at the bottom, brush transfer doesn't go. It's
Oh
like-
fuck. Sorry. Yeah. Yeah. Facts.
85.
85.
Garrett pointed out, or maybe earlier, you have recovery lines in that area below the bulkhead, and you have those flat surfaces. They could get caught, so if you want to redesign them to have some chamfers on them, that would probably
Redesign what?
the strain gauge module.
How big?
Yeah. You have
I- yeah.
in the area that your modules exist, you have a bunch of recovery lines, and the tops of your surfaces are flat, so they could get caught there. So you just redesign them and have a chamfer, so they don't do that.
Also here, I know on, it's like, you can see here, you have the notch, but have like a taper on it. But the lowest guy doesn't have a taper, so I don't know if that matters or not, but just something but that lowest measurement stick doesn't have the same type of taper that you put on the notch as it's on.
There's a
Yeah.
taper piece on the bulkhead.
Yeah.
So every piece the bulkhead slides over, you get
Is
that
taper-
taper.
They're also the overall size of the notch is a bit bigger, like
Okay.
obviously for the clearance. So,
Yeah.
but a taper on the strain gauge modules would also be nice. Just taper the shit out of it. Yeah.
I was gonna bring this later, but now that we're talking about it, that is not where I thought the modules were. I thought they were going on the 10D.
No.
Okay, then we're gonna have to do the thing where we blow up a charge right next to it to see if there's any fragmentation that could
Isn't all of the parachute between the charges and that?
not necessarily.
No.
Uh
I guess it's low enough down that not really. Yeah, good point.
Okay.
Oh, and also I'd be slightly worried about, like, technically it clears, but I don't know if this might be something, but that it's also very close to the candy charge, like when we check that.
We checked the pins will be fine.
It will clear it.
Yeah.
Yeah.
It's hard to
I
see
know
with the
it's above it,
screenshot.
but I just don't know.
No, yeah,
But-
it's hard to see with the
Yeah.
screenshot, but we checked.
I
You
did
do, like,
all.
a limit distance mate and just like watch as it comes out and see,
Okay.
I
Yeah.
theoretically did that. I don't know if it survived
Yeah.
transfer.
No, we'll double check that, but yeah, cool.
Sure.
Next slide.
89.
Oh, and the next one, 86.
You was a
This probably doesn't matter, but you're not limited to integer values of like length to diameter.
Yeah.
We were when it was COTS, like
Yeah.
if 5.2 is better, we can make that, No.
It works, but
Yeah,
Okay.
like also who cares? But
Okay.
That's the thing.
87.
Yeah.
Are we worried about like the antennas and
Oh. Can I say it?
Yeah.
So okay, the antennas are very long. They're gonna be like helix coiled. Sorry, I didn't mention that during the presentation, but they're gonna be like helixed. It'll be cool.
Do
Trust.
you know how to calculate the length for that?
Yeah.
We'll figure it out.
Avionic does.
and that will ensure that there's no interference.
Yeah.
There's no-
The- We'll set It's like here's to like have a different, and the one will be at the top, and then it will be a different one, and we'll just get different things.
For some of these components, your batteries are kind of oversized. If you don't have volume or mass constraints, it's fine. But I remember us having both of those, so yeah, that's a thing you can do.
Thanks.
We didn't have washers in this.
Oh.
There you are.
Where
Kind of everywhere.
you can on that like upper surface, sure, you're probably fine. FEA on the bulkhead will tell you if you need a washer under the iNet. Right.
Yeah.
We're good.
Okay. Yeah, you're probably fine.
What are the handle looking things? So those for like cable run?
Yeah, cable management.
Use that should.
I have some, who's naming that section? Okay. It's like, here's that.
Oh, boss. Yes.
Those ready terminals in the stock goes under.
I would consider 90 degrees on both ends. You might need a spacer or something, but like you might just run into the nose cone, which wouldn't be fantastic.
Okay. Next slide.
This, the next two slides, when are we making the call out to?
The requirements state January, like RPM, the call will be made by this weekend.
I guess. No.
Next slide number.
94? No.
94.
Yes.
Yes.
It's kind of hard to see, but the hole for the thread rod in the center, that looks like it's tapped. It's not, previous years it has been tapped.
Yeah,
Is there a reason why it is?
The threaded rod is through.
Yeah.
Just for that, so that should be a clearance hole.
Okay, we can change that to clamp saw.
There's also no fillets on your clocking notch, which if it's water jetted is fine. If it's CNC, not really. So. Yeah.
Okay, fair enough. You win that one.
Yeah.
So.
I'm stupid. Yeah, sorry. That's the way, really.
So just to confirm, this is 70-75 now?
No, this is 60-61.
The 60-61, and you can't just make it slightly thicker with 70-75 and make it lucky.
Well, the choices are 1/8 inch or 1/4 inch. So unless someone wants to like mill off a whole like face,
I have to do that.
Like,
I was stupid as shit.
you're not
just do that.
You're not saving machining time then. You still need to.
Yeah, you're going to see it. Yeah, but
There's like 4 mils or 6 mils, and there's.
It saves
They have a
me time
bit
because I have to make the flip paths.
Yeah, apply butter.
Oh, no, so we can shave it. That's true.
Yeah, I just.
You
think-
can face mill it to any arbitrary.
Yeah, I just think it'd
Okay.
be simpler to not add a CNC part.
Okay.
When.
Well,
that makes much. How much weight are you saving?
Yeah.
How much was it?
It's an increase in weight from the 1/8 inch 70-75, but the FEA said that wasn't strong enough.
Right.
So this is like the next best option in terms of weight.
Okay.
That still uses like a stock sheet metal.
Is
But
it
we-
strong enough if you use washers?
No.
Okay.
Did you do FEA with washer?
The washer was honestly pretty close to like the base of the INA is already like pretty big.
That's strong. That place doesn't do much. Yeah.
Yeah.
Okay. We'll look into
Yeah.
just making a different thickness for 70-75.
That would be hard on this.
Okay. Next slide.
97.
97.
This is really good. I know that a judge has said, no, swivelings don't work, but like, we kind of show that launches last week that like had a swivel like, it just helps and ensure that nothing gets tangled. Even if it does nothing, I'd rather do nothing.
Is there?
Knowing.
Sorry, is there a
It
potential
really
negative?
does.
But if it does,
If you put any amount of force on that, really does not want to turn. And there's a significant amount of force on this, so it really does not want to turn.
Yeah.
I don't think we should do it.
Yeah.
What's last?
Oh, sorry, 97.
104.
Next slide.
Next slide.
What happens if during manufacturing we increase mass in some capacity and we go above 165?
That is, that the number for mass that I've been inputting is the mass of the rocket times a factor that accounts for it. So I've gone through previous years, seen how much we increased mass by, and added that on.
My goat. All of my goats. All of my goats.
About 2%.
Okay.
That's not fine. I was gonna say.
You know, sure.
Buzz.
I'll make like 5. But
Then we're definitely, if I make it 5, then.
Oh, that makes it 2. Also, is our horizontal velocity at apogee, like, because that's what determines drove. Is that from like our normal sims or from the sims with the worst case wind?
That is from the normal sims.
Yeah.
Okay.
Well, damn.
Good.
Well, that'll just increase the force.
Yeah.
And theoretically, there's
But we should know what the maximum force is.
okay.
All right.
We brought it up.
Yeah.
You got it.
Next slide.
106?
106? 99.
I'd just like to see a calculation and the further drift numbers.
Cool.
Moving on.
106?
104. Yeah, so you say like at top speed, here's how our drag is distributed, here's the normal force that results. At top speed, you also have the greatest pressure difference, which is inside and out. Does this math account for, because those forces will work together, right? They both want to separate the rocket. Do you have both of those, or is this just the drag?
This is just factoring in drag.
Okay.
Isn't that what for the pressure port? What was it called?
Yes, but the pressure math doesn't account for drag, and the drag math doesn't account for pressure. They work together, so yeah. But you can get pretty easily the number from the pressure port math and just like have an addition term here.
Yeah.
Like you'll be fine when you do it. Like do it.
Okay. So no, it doesn't.
Okay.
So the next about this slide and the next slide. Oh wait, or about shipping now. Have a factor of safety more than, or factor of danger more than 3. Like you want to have it explode. No other component is going to fail, and like there's no issue with having it explode. So
Potentially Ryan's hammer eBay.
I mean, we usually round up the numbers, and then our backup charge is bigger. So in practice, our like actual number is like 5. For at least for the second bigger one. I'm gonna stop and slide.
just want to like
Yeah. No, that's valid. Yeah, so like the math says 1.65, it's actually 2.5. So it worked out to like 5. Yeah, you're good.
just one.
Yeah, good point.
Next slide.
You have a thing?
This 106?
Yeah. Sorry.
Yeah.
Sorry. 106.
I understand wanting to switch to vinyl tubing. Is that proven effective? Like, is that a standard practice that we know works?
Yes.
Okay.
From other people, yes, we have not.
Not on
Do
our
it.
team, but
What are
we
at?
we're gonna adjust
Yes.
this. Yes.
Next slide. Do you have a plan for the dates of most of these?
Yeah, what if this doesn't get done? What if no testing happens?
If drop test doesn't happen, oh well. If we don't do ejection testing,
we ain't going up.
So those are the two ends of the spectrum.
Specifically, like the VTOL related stuff, if that doesn't happen, it's not like we're not launching.
no, we're just gonna use the Eventbrite stuff, and it's probably falling even slower than.
Cool.
Well, like this presentation is what we would continue with if we don't do the VTOL drop test. If we do it, then we'll go back and do the numbers. But
Yeah. Next slide.
112.
111. Oh, does the measurements eBay have an LED or some other mechanism to tell you it's on?
So you don't have a dedicated like beeper or LED.
Okay.
Your Arduino does have an LED though, we could just use that, I don't know if we can see here.
If you can you see it from outside of the asset?
You will not be able to.
Okay.
So
You kind of need a dedicated LED right from the hole. It's
And also make your screw switch. You heard that right?
Yeah.
Come out from the
line.
Let's put it out there.
You wanted to come out, like the payload wasn't the gap on it. It's never been issues with the other. You don't think it matters.
have you guys not had issues with it?
No, the on with Event Horizon, it didn't turn on because I assumed something got like messed up when we integrated, not because the school switch was too hot. Like you turned on the other two.
You were able,
Okay.
you were able to screw it in a lot, like it just would.
Yeah, I think something was wrong with like Event.
Okay,
Um,
good for this side. Cool. 112, you said?
The same thing, it was just about LEDs, make sure that you can actually see it.
Yeah, we should be good because it's.
We have holes on like on top of the LEDs,
Yeah, that's true.
so
There's a screw switch hole and there's an LED
if
hole.
it's not on, we'll see it. And if it is, we'll-
Next slide.
114. You say, first of all, sig figs.
Yeah,
second
I
of all,
realized that when we were studying.
like you said, buckling likely won't be an issue. It's a one equation, show it, and then show the factor of safety of 100 because you've already shown that.
The equation like explicitly is not designed for this type of like. Don't you need a certain length to diameter ratio before it's even a valid equation? Yeah.
Yes, but then
This
there's-
is below
there-
that.
then
by
there's,
a lot.
there are equations to verify buckling, otherwise it's like for. You should be good, but like, there are equations to it.
Ron, can you just stand on the other side?
Yeah. I kept on going like that.
116. So you say like, oh, no spinning bay lower body section. There's already holes there. Are 4 and 3 the actual number of holes in those sections?
No.
Okay.
Sorry.
Yeah.
No, the pressure ports in those two sections are just the screw switch holes.
Yeah.
In the nose cone, it's 5
Okay.
quarter-inch diameter holes. In the body tube, it's another shit ton of screw switch holes. Sorry.
I would just do the math for that number and say, with 5 holes, here's the minimum diameter. We're above it. Just to compare.
That makes sense. Cool.
Yeah.
Are there 5 holes to nose cone even?
Yeah.
This is the minimum, but yeah, we'll do that.
Okay.
It'll make it better.
Yeah, that makes more sense. Yeah.
Next slide.
Where are the loads for those factors of safety coming from? Like you just say it without.
So thrust is gonna be on the way up, like the max G is pulled. Drag is actually
So I
get word.
it is the bolted connection between the bulkhead and the payload under various loads. So the payload has some mass, so whenever there's an acceleration, there's a load. So on thrust and drag, it's like pulling up and down. Does it fail in tension or thread shear? I forget which one was worse. Parachute is similar. Ground kit FOS was basically just it's in shear now, and it's like a little bit faster. Yeah.
Was your ground hit number actually right? Just
Like in terms of G's. Yeah. The number I used was 60.
Oh, okay.
Yeah.
Okay.
Both are strong.
We're 121 for a second.
Oh yeah.
No,
I have some for me. Your forces are different by like I don't know, factor like 1.8 or something. You also have accelerations, like those ratios don't match up, and I feel like they should. Yeah. It's a good point. So I don't know which one is wrong, but like I would work that out. Figure it out.
Okay.
Right.
We wrote that one down.
But it looks good.
Oh yeah, the
Yeah.
graphs are beautiful about it. Good shit.
But the.
Notice how I will point out, Jake, standardized like all of the
Yeah.
color bars so they're all the same, like
Yeah.
amount.
That's good.
And you also typesetted both now in LaTeX.
Yeah.
Except well that was
Alright, next slide.
My fault.
125. I don't know if it's still an issue optimization wise, but like your main stress seems to be right there in the center. All of the other parts could be thinner. if we don't care at this point, who cares? But we don't really care.
I mean, I guess we can see how much weight it saves, but
Okay.
I don't.
Go higher.
Okay. Yeah. That's it. No. Like you keep the two.
Like, make
crowns,
these
this
things-
one switches
130.
Oh,
120.
okay.
Yeah, I'm going 129.
I looked at that testing plan, that's like exactly what we should be doing. Or maybe a couple like other details that we probably should have, but like, you know, any tests that people are doing here should look like that. So, thank you. Alright.
You said 130, Daniel?
Yeah. Does everything have to get turned on before the rocket goes on the rail, or like, is there a chance that the rail is blocking one of the screw switches?
Yeah, you can.
That's yeah.
The only thing you wait to turn on is your.
Well, so either
Is
turn it
your-
on very, very early.
Well, I mean, the only thing you should be turning on when you're on that ladder is just your your computer. Because it's on the.
Well, we would also like to turn on cameras and things. Yeah.
But then you can turn those on the ground, like you don't have to.
Yeah,
We
because
can.
either do it very far long before you put it on the rail,
Yeah.
or change it.
For battery life, it would be preferred to do it
Yeah.
on the rail, so I can just check.
Yeah,
it.
just
Oh,
if you just do it immediately before you sign on the wheel. Yeah, exactly.
Yeah.
Like as you take it off that, or even when it's on that thing, like the.
Yeah.
Is it turned on?
Is it also not just simple to check if it's good
Yes.
and add, rotate it slightly?
If I had like 8 of this, maybe, but like I can just make it positioned. Yeah.
Just that case.
Yeah. That's a good point.
134. Sig figs.
Yeah.
Just ignore the digits you don't like.
On Vivo, we just square.
Next.
Oh, wait, next slide. No.
I have 137. So let's try to avoid like messing up like drilling holes, but historically in the past we have, and like there seems to be like a lot of space there to move the holes further away from the edge of the boat tail and the body tube. Could we do that?
Yeah. Now that it's thicker, you don't need to keep it in the center.
Yeah.
Your edge distance to the top of the bulkhead should be the same. So you maximize the edge distance on the tube.
So
Yeah.
Okay,
So the
so
last
side
couple
is-
years when we've been drilling the holes we connected to.
Oh, the interface centering ring holes?
Yes.
Yeah.
Yeah.
Go way like.
We've done such a bad job, there just like hasn't been any material left, so
Oh,
just
okay.
move it down so that we have more leeway.
So make the interface centering ring.
Do the math and figure
Don't
out.
change the centering, change the whole position.
It has to be centered.
This is in the center between here and here. You should move this up, you should move this down.
Yeah.
Wait,
So I
move the
both
top
of them.
one.
Yeah, move the top one up, move the down.
Move them further away from the edge.
From the, yes.
Okay.
Okay, part of that.
Can you just like rehash that easy note taking?
Move the both of them. I'm gonna wait from the center of that.
It could not possibly be clear.
They move the bolts further away from the lip of the interface centering ring, and I will know what that means.
Okay, do we have the casing, to ensure that the lip hits the bottom of the boat tail, so that we don't have to do a layup like that?
Yeah.
We had it like here,
Yeah.
but.
Yeah.
If you-
Yeah, we own the case.
The motor's got that motor down in the back of the bed.
Yeah.
We're not doing either.
All right, next slide.
Next,
138.
138.
Okay, found it.
So 142.
I don't, this might just be like an apartment, but I think Gordon brought it up when we were doing the line testing. Why do we have to use the lathe to do the threads? Why can't we use a dial?
We could do that too.
Yeah. I spoke. Jake's been practicing. He actually just showed me a part in that little break where he's been practicing the external threading. If it proves bad, we'll probably just go to a die, but it is an extra like, I want to say around $40 for a one-time use die. Just kind of,
We have to make 2 of them.
one, okay.
Go back one slide. For the old Finstock, do both know the procedure that you made it, and is it the same procedure that you're gonna use this year?
So, yes, we know the procedure, how we made it. Two, the procedure we do this year is based off of how this testing goes. But, like, yes, one thing I realized while we were saying that I should add, it's not 0.3, it's a bit more than 0.3.
Sure.
We meant to make it 0.3 and
Well,
it ended up being bigger.
This area of that itself was it was close like 0.31. The area within themselves because of the tip to tips was bigger.
Oh.
So this is actually very close to 0.3. It's the fins themselves.
As long as it's the same thing.
Yeah, it'll be the same. Yeah.
Are you guys doing this testing, like, when do you guys plan on doing this testing?
The goal was
Like, this shouldn't be an expectation.
well, the goal was to do it before then. I don't know now how great that's looking.
Okay.
The like ASAP because we have to stop.
Yeah.
We just need to make it.
Okay.
So
I assumed it was before because otherwise it should be.
no, yeah, the goal is before our event, but we'll see how that.
Moving forward, I just need more dates. I just need a little bit more of like we have the urgency to get this stuff done.
Next slide.
149. You have said that you like don't know exact temperatures. Did you just put random, or did you look at like Ohio or Columbus?
It is the average temperature during whichever month. So for TMO, it's April. At TMO. Yeah.
I probably should have specified that instead of just saying vibes, but
It's still, yeah, it's the average. Next slide.
156. Just want to see. Look at it. 157. Yes. That 4K same from Q.
yeah, it's 1,000 feet up, so we rounded down.
And then I've done this before, but show open rocket stability graphs. Like I know,
Right.
Doesn't want it, but like
Double-
a lot of this IRAP doesn't.
Yeah. Next slide.
What's CC? Just because this was brought up right before, CR, the minimum factor of safety on load variable.
Yeah.
Is 1.6.
I was gonna say, since that's kind of we're planning on changing that after some thing like it's still. in a way.
I don't know if so this might be.
Okay.
Well, we'll deal with that. But
Yeah.
that should be updated. Yeah.
Yeah.
Next slide.
Oh, what was the next slide?
173.
It's got FBA. Oh.
Oh.
There.
Get in and wrap
No, I had to grab my gloves.
173.
Yeah. First and foremost, keeping in mind that we haven't had a measurements team before. Everyone else has stuff they can look off of. He doesn't. That said, what is the housing man?
Petchy.
Okay. Is there a reason you have those like billets?
This yeah.
It's printer reliability. So as the printer prints, right?
Yeah.
The gauge has to accelerate as it goes through sharp turn. And while that happens, the slicer has to account for the amount of material deposed.
Yeah.
So if you have nice swooping corners, it'll be it doesn't have to accelerate.
Yeah.
So that's printer reliability. Yes.
So do you need that like circular base there? Like
It doesn't necessarily have to be circular base, but it would the corners have to be rounded off anyway.
Sure.
There's a lot of more surface contact that have with bulkheads.
Is there a reason why it shouldn't be circular or?
That was more like a curiosity.
Yeah, so
I mean,
it's
that's
just
just
for the last space. I mean, it's not
Also,
like
like not circular, like there's like these extensions for the threaded rods. Yeah. I don't know. It's having a rectangular. Keeps it. I don't know. That's what I was thinking.
Like the profile of your cap. If that was just your
eBay
eBay all the way down, it would probably
it's
be
been
fine.
hard. It would set wall.
Yeah.
So it's kind of like a multi. It's just a different type of.
How much could you shrink this? Like, because the battery, you can't make it shorter than the batteries, right?
Yeah.
Like, how much shorter could it be if you had extra amount of data download?
I couldn't give you a number, but I work with that. Is there a reason to shrink it?
Okay, table this.
Okay.
Go.
Sure. Okay, is there next slide?
Next slide.
I will say, why number 8 rather Raj? Like, was that based on something?
And sorry, CodeR, PDR. I did calculations, and then Gordon came up to me and said, just use number 8. So I was like, okay. It is.
Nah, I saw it. Okay.
Calculations with the number rates, or did you just?
Well, Gordon said so.
Calculations, though, or was there an issue with?
The issue was that first of all, I had like a ridiculously high factor state. It was like an 80. So like, I think it was just I didn't go for the exact minimum, but I was working on. There was a lot of assumptions made. Gordon just said that those should just be reliable for what you're using. Okay, next slide.
175. Say there's a voltage shifter, then
Yeah.
know that there's a voltage shifter.
Yeah. Next slide.
Make sure that when you're like actually attaching the epoxy and attaching the super glue, it doesn't mess up with pins to the point of capacity. Really, it seems like a really small, right? Make sure that nothing. That's not.
I guess talking about like just this gap here of
Yeah.
inserting.
Yeah, we're inserting it like, and like the pins themselves, if they're messed up.
Next slide.
So. They all look very similar. Add some like etching or like note or on the actual like each shoulder so that you like someone can pick it up and know this is for the
Okay.
I'll just put the text on.
Yeah, add
Yeah, you can just print text into it.
Yeah, just add something.
Next slide. Or
182.
182. Anything before?
You say ABS because they're close to the motor.
Yeah.
Are the ones on the body tube also close to the motor? I'm not glad I don't.
They're close to. They're not as close to the motor, and what I meant to say is since it's close to the bottom of the motor, just if there's higher heat there. Also, yeah. Next slide.
190. 185.
185.
185.
My thing was like, or you have, it goes into 186, but like make sure that where the assembly for all of that is in the drawing, so no which points and we'll talk like that. But so like add permanent fixtures that you can't do. Other stuff like actually good for stuff. That makes sense.
What do you mean, like, sorry?
In the assembly drawings, more like make sure that the process of how you actually want to put all the like modules in, as well as what has to happen, what the modules have to do before you put in like bulkheads or other things that are permanently affixed. Make sure that it's in the drawing step by step.
You explain this, but I got use not the line. So when it comes to actually like putting this thing together, the only thing that you're really going to be aiming to do, like when we're integrating the rocket and comp, is just like the wires,
Yeah.
those connections.
Yeah.
So all the modules will be in those, so they're meant to be those meant to be.
Yeah.
Okay. And are there any wire connections? Which ones are the wire connections you can make prior, if any?
I was thinking we can make at least do the soldering on the actual strain gauge boards themselves. I mean, and just have them when on transport, just have them like lying in the tube. So like for example, I didn't mention this and I'm sorry. I do want to have like a cable, like a proper cable running from this ADC to the eBay. So we can have that cable already have its connections to the ADC and those strain gauge boards. And then of course at comp when we at comp there will be enough slack in that cable so that outside the rocket we could attach
all those wires to our connections in the eBay and then insert the eBay. So like something like that.
So they're already openly taped down, right?
Yes, it will be taped.
The strain gauge, right above the motor. How easy is that going to be to like install? Are you kind of like reaching in a decent amount and then sort of like?
Yeah, that'd be the way we do it.
If you care exactly, the problem makes sense.
Because I guess the location doesn't matter.
Well, I was about to say from the top to the thrusters with overhead is like reaching the limit of what you can reach with it, my arm at least. So if you, depending on how far I'm gonna put them.
But the precise location of it doesn't matter.
Yeah, I was gonna say that. Like as long as it's just below the thrust transferable.
It doesn't even matter the line, as you know.
Oh yeah, it's not hot.
The rest of
We'll have Paul's phone
Yeah.
189.
189, anything before?
Oh, 186.
186?
I guess it'd be nice to know like what drill size you were thinking of using, or like what hole diameter you need
yeah.
for the wires.
I'll talk with their specialist about a specific diameter. 189?
How sure are you that you're not gonna have the wire separate from the VGA terminal and not like if look at that again the above picture, how you sure it's not gonna break in between the terminal and like just the wire, like the wires are just gonna come.
Oh, that terminal. Okay, yeah, the picture's doesn't show that exactly, but this is like the actual VGA cable, like the cable that already has the terminal on the end.
Like an existing thing with like the plastic that
Yeah.
Okay. I thought it was like literally gonna look like that.
Yeah.
I would still test that. Like someone put that on loads and like pull on the wire and that would put this whole setup and like solve it and make sure that it's not gonna break off from the wires aren't gonna break off the connector.
I know when you like use VGA for like custom stuff like this, you have to like cut it up and then like splice it into your specific usage.
Yeah.
Have you like done that? Like
Yeah.
Okay.
And
So
we
that's-
even soldered like
Oh, cool.
other wires too. So.
I've done this with the USB cable.
Okay, it's pretty doable.
It's very
Okay.
easy.
That's it.
And then also, so that your solder joints don't get loaded, you should make sure that this cable is somehow tied off or something. Like, because like if this cable is free floating, and then it's like its only connection to the nose cone is just solder joints onto an PCB, then it's just gonna rip the solder joints, like
Okay, yeah.
because once it fully extends to, it's gonna fully extend and then it's gonna desolder itself, right?
Can we just
So-
tape it to the side of the nose cone, or do
Well,
you want to?
You could. I would recommend if I don't know if there's anywhere in the nose cone, the best thing to do would be to tie off that VGA cable somewhere. That's not possible. I would like glue a good long length of it, like 4 inches to the thing, like the cable. So you like glue a good length of that to something so that part so it's getting glued, and there's still slack between like the cable has slack in it between where it's glued and where it's soldered to the.
Three concerns I have from a standpoint. One, is it going to be able to separate easily while still like staying in during flight? I think we've already covered that, but I just want to
Yeah.
make sure that.
I mean, like the VGA.
You just need to do a lot of testing
Yeah.
of like, let's say with shaking and stuff and accelerations that will work, and then when you pull with all those
Not
things.
necessary.
And the reason why we chose this cable, apart from the coming from a BPS space video, is that even just attaching it with your hand gives you like a decent connection, right? You do need like when you're trying to separate a VGA cable, you do need a decent amount of force to separate it.
And sorry, go.
No, that's the end of it. Like,
And there is value in saying like this specific setup has been used like
by Joe Barnard.
Yes, like to solve this exact problem. This isn't shoehorn based on some other shit. Like it did this. It worked.
We just have to do our own testing.
Yeah. Yeah. Sure.
Thanks.
Wait, the other
two things.
one or two, however many I said concerns I have. When this does deploy, I want to make sure nothing breaks and can damage the parachute. Also, I wanna make sure that the cable which is flailing around isn't going to rip a parachute while it's being deployed.
The other concern that I have is that
That too.
Okay, if we turns out that these are things that we don't like, to the point of gluing the length of the cable, you could glue it all the way down to where that couple of stops, and then only have like the 6 inches be slack.
yes, let's move on from that. We can let's move on.
This
Next slide.
Testing. Is this based on tools we currently have, or you're waiting until composite manufacturers tubes for the IRIC routing?
I think this is a mistake wording there, because the next semester after use this.
No, well,
Well, so if you're planning on doing this testing for this year's rocket, while they are manufacturing, you could just take one of the end pieces.
Yeah, that's-
Yeah, I mean,
Yeah.
she doesn't need that. Yeah.
Well,
You just.
yeah, what I'm saying is ask them to manufacture it a little bit longer so that you have a decent chunk instead of just like the slight even on the end.
It's in our body too, like as long
Well,
as we can.
we
get
did-
that.
well, yeah, but-
Or you can, or if we have enough material to do like just one.
Yeah, have them practice, then we
Do with the second process. Same.
And
Yeah.
Next slide.
195.
93. You guys said you didn't have these yet, or like you didn't know which one you're gonna use yet?
Yeah, we have an idea just based on like what we talked with like Drew about what they used in air brakes, but
Okay, just get an idea like ASAP, cause I mean, I don't know how fast this is, but just for the sake of procurement, I don't know at all.
So I will say for these, yeah, it honestly, like I'm assuming you're gonna like when you say you don't have an idea, is it like you just don't know what type you're going with at all, or you don't know what like specific W25?
Well, because we have the ones from air brakes that we can use that for testing it, and I was
I
thinking
would check.
we would use. Yeah, no, obviously, but like I was thinking we could use the same one that Payload was gonna use.
Okay.
Because that
That's
seemed
it,
like
that-
good capacity, good rating. speed.
Fair warning, doesn't really affect anything. That is an SD card.
But isn't it the one that's like soldered in?
Yeah. So just in case that changes anything.
No, I'm aware.
Okay.
And that might actually be easier because it would be helpful to have the file system on.
I would use that one anyway because it has a giant capacity.
Yeah, so that's what we.
And that's the only part you really like kind of stress stuff.
Yeah.
All the others are good.
Yeah.
Yeah.
Next slide.
95.
95.
What is the shielding method of the wires? Like you said you had shielded wires.
Yeah.
What kind of those?
So I've looked into this. We can either buy wires that already come with a shield that you just with an extra layer of protection that you just ground to. Yeah. Right, next slide.
So. I just want to verify her efficiency where.
So this number is actually I actually got this number from Ryan, but I know that the buck converter has an efficiency that they label on their data sheet of 95%. So this is like
80 was just as like very so
Okay.
that it should be high.
98.
More question for you than for Karthik. Can you walk me through why the first thing you do is copy your data from your first flash to your second flash?
Well, I like really don't want to ever be able to lose the data. So it's like at some point the flash needs to be cleared, and it's like if that happens when the Arduino resets, like we don't want to have any chance if someone like accidentally resets it or bumps the button when we're taking it out for that flash module to ever get reset.
Okay.
That was the idea, just data redundancy.
So that makes sense. The only thing is like, okay, so this is more because my concern is like, if you're doing that, cool, but if like that goes wrong in flight, that's not gonna save anything, like it's
Yeah.
not gonna resets in flight, because when it lands, it's going to also, I'm assuming clear flash one, right?
Yeah, I mean, honestly, what might be better, because I think we're looking at about like 5 to 6 megabytes of data for the whole flight, is to just get a flash that's big enough that we can always add to it and just have a file system on there. That might be easier.
Okay. The second question that I had is how are you retrieving data?
So well, the data we're gonna just store directly onto the flash, and then I'll write a separate program that we'll put onto the Arduino to get the data back out.
Okay, fair warning. One of the things that happens, if you're using SPI flash, which is what all of these boards are meant to use, when you initialize the flash device, is it in the most common method, it wipes the flash chip. So that's why for air brakes we didn't try and retrieve it directly from the flash. We had a separate SD module that we could just remove an SD card for. I think that just might be easier. Regardless, it's not much extra steps, so consider adding an SD card module.
Yeah, sounds good.
Oh, okay.
We're on the program.
Flash?
Sorry, 200 and 201.
Oh, yeah.
So, can I just pause all of our FMEA concerns and we'll talk about that when we do a proper, like, we for you to have FMEA for both measurements and payload style. Yeah, and we have to redo FMEA. Let's table this and talk about it then. Okay.
Alright, next question unrelated to FMEA.
You can go through to the next slide after FMEA. Okay, I got it. I have something for you, like requirements wise. I may have just misread stuff throughout. But I feel like is there a different requirement for battery systems for different systems? I don't. Sorry, like, is there a different charge capacity, like requirement for number of hours for charging for different subsystems? So, like for number of hours you can live on a system. Yeah. Yes. So yeah, it'd be like based on okay, because
measurements isn't recovery critical, so yeah, it's not true.
Okay. My comment is about 1.2.2-2. Wires will be secured from my disconnection during flight. Securing should probably be more actual. Well, I mean, like, you should say you're securing by zip tying or this or that, and also like if I tug on a solder connection, think of just
it
is.
It's already secure. A better answer there would be like Chris's point of like working in fluid, so the solder doesn't take the load.
There is some between, because we actually do want suppliers to. With a BGA,
If you want a big bop about that, you should.
Okay.
Non-secure to prevent unintentional.
Yes.
Undesigned.
Okay.
Good.
Okay.
Uh, 207. Why does it need to be black?
What do you mean? Why does it need to be black?
Like Ashley.
It's awesome.
Is it
It's a benefit aesthetic.
No, yeah, it just looks cool.
Cool.
It sheds heat faster radiatively. It's
Next
Um,
slide.
Actually, I'm gonna mention it regardless, but when you're updating the GPS traces, do you already have like a plan for that? Like you already.
No.
Okay.
Well, I know what needs to happen. I haven't done it yet, but it's not gonna be that difficult.
Okay.
It's wired wrong.
It's swapping 3 traces. Oh, it's really just 2. We're just getting rid of one.
As we talk about that, like it's important. The reason why the trace wasn't the right way in the first place was like a small, like, one thing some didn't notice, right? Like it was like one thing over one pin.
Yeah.
And I think it's should have a plan to make sure that when we are changing anything like that, multiple people review this side for the spending money.
Yep.
Are there any changes for S2 that will require a bigger footprint?
The footprint's probably just going to be different. Well, because we're not ordering it this year, so it doesn't matter for this rocket. I'm not attached to the current dimensions. Like I'm willing to change them.
I guess so.
especially because it's a major iteration.
Yeah.
Yeah.
Uh,
Next slide.
Next slide. No.
208 or 209. Okay.
Sorry.
I see.
Oh yeah, 209. Your without common filter error plus minus 1 meters, would that account for drift after passing through the barometer, the transonic and supersonic regions that affects the barometer, which is something that is maintained even after you pass through that, just because it shocks the sensor like so much. And
Yeah.
That's why we have the Kalman filters. Like, I mean, yes, like it's important to know when you're know stuff when you're going through the region, but the main issue is that after you exit it, you still are feeling the effects of that. So that plus minus 1, I'm assuming that's not after, so you haven't tested it.
Yeah, we haven't tested supersonic, so
Okay, yeah, so I would make sure you know that there's a caveat with that. Like, I know plus minus 1 is still very impressive, but there is a caveat with that in that is for subsonic points only.
Okay.
Was that 30-second lockout only for the competition rocket for Aurora, or is it just jet?
we can change it.
Okay. Sure.
Next slide.
People have.
I have a blank, so
I have 218. Maybe 1418. Have you gotten GPS fix more than one has? Have you got it?
Yeah, it's consistent.
Okay. Have you got it indoors? I know it does. Like that doesn't matter for my test.
I don't think it's ever been done indoors.
Okay. But it's if you had it multiple times.
out of curiosity, yeah, 3D log, very good.
Yes. Anything else?
What common filter you say is certain error bound? Is that the 1.5?
Yes.
Oh, yeah, you might not be able to answer this. Serena, your because I know she actually working on solid filter. But in its current state, does it just like what is it? Does it just use I'm assuming gyro and magnetometer?
Yeah. Well, it doesn't use any secondary error correcting sources. It's just it's purely IMU. Which is gyro and
Oh, okay.
and inertial. You said 222?
Yeah. How have you verified that you got correct apogee detection if you don't have a second flight computer to that like you trust as comps?
It is currently it's just based off of the agreement of all of our sensors that we slowed down and we stopped having an upwards velocity. Acceleration was not out of the ordinary, pressure decreased at the time, and yeah, the agreement of the sensor. Pressure leveled off, then decreased.
Wait.
Or in
Okay. I'm really thinking about how the pressure. I just want to make sure.
The pressure decrease level.
the altitude
Whatever.
leveled
Yeah,
off,
we get it.
decreased, pressure leveled off.
They have
pressure
that
decreased.
please.
Okay.
I know. I have just for 224 and 225, so one thing.
Oh, I have 222, sorry.
Keep up.
That 1.5 number.
Yes.
Has it like is that just like we can add multiply by 1.5 and it looks good right now? Because like
Yes,
you know by
exactly.
any means, like you don't know it doesn't have to be linear, it doesn't have to be any of these things, right? Any of those issues.
It's very preliminary. Said 224.
Yeah. Don't have something say that it meets the requirement if you have it like fully passed the requirement. Like if it's like this kind of says it's unsupplied flight data, but like 225 you got like for a flight and haven't done for a flight.
Yeah, no, that was just an error. on our part.
Yeah, make sure that what you say passes has actually gone. What you count as rigorous testing.
Yep. Okay. That it? RS matrix, anything about this? Oh, that's right. That's right. I saved it. Okay.
Oh,
Can I get like another round of applause for all of the leads that have worked hours on this thing and been sitting here? Thank you all for being here for 4 hours. Thank you for all your questions. Yeah, have a great night. And,
Trying like my even it's a win.